So, hi everyone, good evening. Yeah, so welcome back to Plan 252, Transportation Modeling. So, I will share my screen here. Okay, so, right, so today's agenda, we will discuss a few things about IFN. So, at the end, you will present your final project. Uh, we'll discuss IFN from Markov chain and then IFN equivalent, IFN transport itself, and then how we calibrate, and then we do some policy centration based on IFN, and then analysis of the policy, especially the long-term policy and optimization of policy combination. So, wait, I have here my Excel. Can you see that? So we can start with generating random capacity matrix. Okay, so we generate random capacity matrix. How many nodes do you want? Say I have A, B, C, D, E. Let's make it 5 nodes. Okay? A, B, C, D, and E. So these are the capacity matrix in number of lanes. Okay? That means, so I will put n underscore random capacity matrix. Okay, so I close this. So only one, and then we can highlight the whole matrix. Okay, and then you click in this part, and then Shift Control Enter. So there you create a random capacity matrix. Okay. So then what happened is if you go to this formula and calculate now, okay, every time you press this button, calculate now, you will create a new capacity matrix. So if you want to visualize this, you can create, you can put it here. So I have nodes. So I have X and Y. So the nodes I will just copy. Right. Okay. So let's say I will start with 50. X maybe around 300, maybe. Let's see. Around 300 and this one around 50. So then we can say this one the same thing. So I will put the same 300, and this one is this one plus say plus 50. Yeah. And you can have this one plus 100. Okay, I just copy this. And then the last one may be around 500. And then I will just copy this. Oh, this one. Okay, so these are the coordinates that we can create to draw. So I will just draw that. N underscore draw network. Yeah, draw the network. I'll get this and the coordinate. Oh, there. Okay, so this is I needed to be on a live site. So what I need to do is just to increase this. So I increase this become 400. maybe I will increase to 500. There. Okay. So if this is too little for you, you can just add. For example, I have this one is plus 100. Right. So the same. So this one I will add this one plus 100. Yeah. And you see, every time you calculate now, you will generate new network in Excel. And so this is how you create the capacity matrix. Is this okay, or you have some question about this? Now, once you have the capacity matrix in number of lanes, okay, now let's set up some parameters here. Okay. So what is the number? What is the first parameter? I think this is in lanes, but when you want to create congestion, so you need to divide the flow with the capacity, which is supposed to be in the same units. So in that case, lanes must be you scale, yeah. So scaling capacity, okay. So say 1,500 is the PCU per hour per lane, right? This is again we can input or you can change this value later. So now I can create the same capacity matrix, but here is not lane, but PCU per hour. Okay. I'll just copy this. So let me move it a little bit there so that you can see. This one is 450. Okay. So with this, okay, what we will do is we multiply. Let's give name of this. Let's give name of this in here. Scaling capacity. Okay. Then here we just multiply between this scaling capacity with capacity itself, right? So now you have the actual capacity in PCU per hour. Okay. Of course, let me give a color. So I will color this with yellow. So this is the input. Yeah, this is the actual input. Yeah, the number of lanes is to make it easier for us. The actual capacity matrix must be this one. Okay. So let's keep this name C underscore. From there, you can calculate the flow matrix. Right? So the flow matrix also in PCU per hour. PCU per hour. Okay. So you just copy the same label so that you will see. Okay. You copy the same label. So what I will do is n underscore capacity to ideal flow. Oh, now if you want to make this capacity to ideal flow, there are two parameters. One is the capacity matrix, The other one is the total flow. Let's define the total flow first. Total flow. Right. So I will say I will put 1. At this point, I don't know, so I'll just put 1. Okay, again, this one is PCU per hour, yeah, but not per lane. Wait, let's name this kappa. Okay. So now we can, once we define the parameter, okay, now we can define the flow, right? So n underscore capacity to ideal flow. So capacity is this one. And then the kappa is this one. Okay. So then you highlight the whole matrix. Click in this edit or F2, and then Shift Control Enter. Right? There you get the sum must be pretty much it. Okay. So let's do this. So the sum must be pretty much it. You can start to see. And the total must be 1. Yeah. So I will just color it differently so that you can see. Yeah, this is the sum, which you will see these are exactly pretty much. Yeah, this 22, 21, 22, and so on. Of course, because this is random, so every time you change formula, calculate now, it will generate different values. So if you don't like this one, now if you know what is the total flow, yeah? Say after you do the base scenario and then you already know what is the total flow, say, then you just type here. Yeah? So for example, I have total flow of 17,500. Then I will get this value of ideal flow, which is 17,500. Okay, so let's make it simpler. Because it is flow, right? This is just formatting. Huh? I'll just remove the things behind the column. So, and now you can find a congestion matrix. Yeah? C is the congestion matrix. So this is unitless. So PCU per hour divided by PCU per hour, right? So this is congestion. Yeah. I will copy and I will copy also the ABCDE. Okay. So what is congestion? Congestion is just Hadamard division. So n underscore Hadamard division of the flow. Oh, let's keep name first so that you can see. Let's keep name of this as F underscore. Okay, so then you can put here equal n underscore Hadamard division of the flow and the capacity. Yeah. See, F divided by C. Okay. So then you highlight, okay, and you edit here and that up. So this is the okay. This is the congestion. This is the congestion matrix. Here, in this case, if you set up, if you set up 17500, I will have maximum congestion. So let's get the performance here. I have maximum congestion. Maximum congestion is so max. Oh, let's keep name G. So let's keep name G underscore is represent congestion. Okay. So then we will have equal maximum of G. Okay. This one become clearer. Oh, because this is random, so every time you move, it will change new one. Okay. Sometimes it will become 2, sometimes it will become whatever higher it is. Okay. Okay. So now I want to set up, okay, at certain values. Okay, so we don't want random. I will put the random values here. Okay, but I want to copy these random values. Okay, I want to copy this to be. I can generate again, yeah. So this one, and then I can copy this. And I'll delete this one. And then what happened is I copy this one, the random value, and then I put here as paste as value. Okay. Yeah. So once I paste it as value, you can see these are numbers. And it will not change anymore. Yeah? So if you change the formula, calculate now, only the random number will change, but the velocity will not change, but everything will be fixed. Yeah. Now, you can see the total flow is very related to the maximum congestion. Okay, so these are the one that actually very related. So if this is the base scenario, what you will do, I need to set up certain maximum congestion. Okay, so for example, I will set up this as 0.9. Okay, so how to make this 0.9? To make this 0.9, I need to change this total flow. Okay, so what I will do is go to data, what if analysis, and goal seek. Okay, so I want to set up this maximum congestion to 0.9 by changing cell the total flow. Okay, it will run. So for this network, on this network, to make maximum congestion 0.9, see 90%. Okay, the total flow must be 13,500. So, and then we will name this as this scenario. This scenario, yeah, now I copy this page scenario into the new one. So copy. So let's name this alternative scenario 1, right? So L1 scenario. Because this is copy, of course, everything's still the same. What happened is I will not, at this point, I will not change this one. Yeah, I will not change this total flow. So I will lock this one to become blue. Okay, this is the one that I want to know. Okay, then what I will do is I need to change the network structure. Oh, okay. What will happen if, for example, look at the network here. What will happen if EC, for example, EC, this one, 2 lanes, okay? What will happen if 2 lanes now become 3 lanes? Okay, so I change this one to become 3 lanes. Okay. So when this become 3 lane, apparently the maximum congestion does not change. So this is actually useless policy. Yeah, you compare this on 2 lane a while ago. In alternative one, I changed it to 3 lane. So this is not so useful. So let's put it back to 2, okay, because it doesn't change. So then I said, okay, in that case, I will remove, because this is the one that bad. So I will deal with DB, right? This one, DB. So instead of 2 lane, what will happen if I change this to 3 lanes? Okay. So, yeah, of course, maximum congestion reduced to 60. Okay. For the same total flow. So this is a good policy from congested, not congested. Yeah. Once you have the congestion, okay, of course, you can calculate the other performance. Okay. So if you want to get the performance of delay, minimum travel time, get travel time, and so on, so you can also do so in here. Okay. So, but up to here, is there any question? Yes, Vincent, yes.
Sir, on the drawing the network, I didn't get the instruction on doing this.
Oh, the drawing the network. This
Yes.
one. Oh,
Yeah, and draw network.
you just pen draw network, and
Okay.
then you get the capacity matrix, and then the node coordinate.
Okay. So the first argument would be the capacity
Yes,
as number of lanes.
yes, yes.
Okay. Thank you, sir.
This is also in the manual. I think you can check the manual. There's the manual. Lab manual. So in the lab manual, well, okay, so this is the lab manual, right? So I think that here, yeah, the syntax is the F and the nodes. Yeah. Yeah. So it's very important to understand the concept of this redistribution of congestion. So the meaning of redistribution of congestion is now I have maximum congestion shape on 9, okay, and I can point out where, right? So here, DB, where is DB? Here, yeah? This green line, isn't it? So when we change this, dB now become 3. Now, for the same net total demand, same total demand of 13,500. So now I got reduced. Then you can compare. So all the others are the same. So 25.7, 25.7. So only this one changed. In this example, this is just one case study. Up to here, is there any question first? If you can, show your work, okay, some of you, and then share your screen so that you can see that. I can see that if you understand or not. If you don't understand, I can help you. So the thing that you need to remember is to get the congestion, you need to define the flow and capacity, okay, at the same unit. So remember, congestion is unitless. So some of the mistake that people do is you get directly from lanes and then you divide. Yeah? So you will not get the same value because this is in number of lane and this is in PCU per hour. So the congestion is not unitless. Well, the proportion is still the same, but the value is not the same. Yes, yes, go ahead, Vincent. Yes. You want to ask something?
Yes, sir. I did for the draw network, but it's not showing.
Okay, so let's see. I will stop sharing. And can you share?
Okay. Here, sir.
Can I? Oh, because you did not put the notes. A, B, C, you should put from
Okay.
B to D.
So this one, sir.
No, 3 of them. Yes. Yeah. Enter.
Okay. Okay, I just add until here.
You just change the coordinate.
On the coordinate on the.
Yes. So that coordinate you're supposed to handle manually.
I see. So this is where those nodes will be plotted on the.
Correct. This is just to help you to plot. Huh?
Okay.
But it's quite nice that you can plot in Excel. Yeah. So
Yes, sir.
for small network, this is helpful because you can see and then you can play with these numbers. Yeah.
Okay. Yeah, I just follow what we did. So first we set maximum congestion and then here on the data,
Very good. Yeah.
what if analysis, seek, then set cell here, this one, and then to value of 0.9 by changing total flow.
Yeah. So now you can also calculate the delay. Yeah, minimum travel time, speed, and travel time.
Okay. So here.
Okay. So there's a function called delay. So To get the delay, you need congestion matrix.
Yeah.
You need to create two more matrix there. Yeah,
Speed matrix.
delay. Yeah. One is the maximum or speed. Yeah. The other one is the link. Okay. Yes. So you need two more matrix. So let's call this L. Yeah. That's in kilometer, right?
Yes.
And then the U represent the
Maximum.
U represent the maximum. Yeah. So now if you want to create the U, okay, one way to do is to set up two parameters. Yeah. So we can create the U, which is the maximum speed, based on two parameters. One is the intercept and the gradient. So we can create based on the number of lane. For example, you can set up parameter, so intercept of maximum speed and gradient maximum speed. Yeah. So you intercept, yeah, intercept maximum speed and gradient maximum speed. Yeah. Max speed gradient. Gradient and intercept, right? Say, for example, maximum speed gradient is increase one number of lanes. How much it will increase the speed? So intercept means at zero, at zero
Zero number of lane.
number of lane, supposed to be how much is the maximum speed? Say, for example, 10. So walking.
Okay.
No lane, so people can start still walk at 5 or 10 kilometers per hour, right? And then the gradient you can set, for example, 15 or 20 is up to you. That's you can create your own model. Okay, so in that case, U now depends on the number of lanes. So the C lane available. So you do one by one equal, and that one is delete.
Okay.
So equal, and then intercept of the maximum speed.
Let me set up the value.
Yes. Intercept max speed. Okay, and then that one is gradient max speed. So, and max speed. Okay. So then the U is equal to the intercept max speed. Okay, and plus gradient max speed multiplied by the C, which one
Number of lanes.
Number of lanes. So then copy to all. The percentage you change it to normal number. General. Then I think how many lanes become 200 or 9?
Lanes.
So probably you want to change the gradient, reduce maybe like 15 or 10. I don't know.
It's still high.
Very big, yeah. So
Let's try 5, sir. Yeah.
5 is too low. 9 lanes, only 55. That's too low. Right. So I think 10 is probably okay.
10?
Yeah.
It's 100 now.
Yeah, 109 lanes. One way, 9 lanes. I think it's more than that. Right?
Now for C, it's
For the C, you just put binary. So you delete C with C.
I don't know. For the L matrix.
For the L, you just delete everything and then equal.
I can use green shields.
No, this is just the length. Link length.
Okay. Length. So this is in kilometers.
Yeah, this is kilometer. So in that case, you just binary. So So in this case, equal n underscore binarize
Nice.
of the lane, the capacity of the lane.
This.
Yes, the whole things,
Ah,
the whole matrix. Binarize. Okay, I'll close it. And then you highlight everything.
sorry.
Oops.
I have to do it again.
Okay.
And binarize.
And under binarize of the C lane. Okay, and then close it and then shift control F.
Again.
Yeah, the percentage you put it in. So here is the binary. So you assume 1 kilometer. If you don't like it, you just multiply by any random number.
Okay.
Yeah, so that's okay. Right? So now from there, once you have the U and L, so you can calculate the
Time
minimum
matrix.
travel time, the speed, and then the delay. That's a new matrix. So T0, okay, is a minimum travel time. So you want it in minutes, that's fine. Yeah.
Okay. Copy this one.
And that is
T0.
0 is in minute, for example. Okay. Now here is the equal n underscore, right? This is our, be careful, you need to delete that because this is a matrix formula. You need to delete this, yeah. Okay, so now, so in T0, what you will do is, no, this is one by one. Okay. So equal, okay, n underscore minimum travel time. N underscore minimum M. Oh, there, the minimum travel time is there. So the U, which is the, in your case, F25. No, just one. So this is a scalar. Yes, and then comma the length. In this case, the P, yes, 32. Okay, then close it. Okay, and then you copy Control C to down and Control C to. Yeah, is that correct? Yeah. Now, oh, sorry,
It's
this is
still
still in hour,
in
so
hours.
multiply by 60. You multiply by 60 and then copy again. Okay, so that's in minutes. Okay, the same thing you can do the speed. So speed depends on two, congestion and maximum speed. Okay. So you can put it V in kilometer per hour. V in V is the speed, okay? Yeah, just delete. This is again scalar, so equal n underscore speed S, okay? So this one depends on two parameters, which is G, which is the congestion, yeah, and then the maximum speed, scalar. Okay, close it. And then you to all and down. So in kilometer per hour, right? And then what you have? Travel time. You have the travel time exactly like that. Okay, T only minutes. So yeah, you delete. So this one, travel time depends on G, U, and L. So N underscore travel time. P, L. And then travel time is G, and then U, and then L. Okay, close. Finish that copy. Okay, and the last one is delay, right? This one a while ago is already multiplied by 60.
Not yet, sir.
Okay, I think you need to multiply by 60 to make it minutes. Otherwise, it will be in hours.
Yeah. We're not comparing apples to apples.
Yes. So
Okay.
remember, the formula is just giving it exactly the same units. So if you want to change the unit, so you need to multiply with the conversion factor.
So this is just subtraction.
Yeah, you can just subtract the T minus T0, or you can use delay. It's the same thing.
Okay. N underscore delay.
N underscore delay. Delay is similar. So GUL.
And L. Then multiply by 60.
Yes, multiply by 60. You will get exactly the same value.
Yeah.
Yeah. So that one in minutes.
Okay.
Okay. So now you want to get the performance. Okay. So what you want to get the performance is average or median or standard deviation, right? Of delay, of the travel time, of the speed. So be careful because this is in matrix, there are a lot of zeros, okay? So you cannot just use average. So in IFN, I already provided N underscore, I think positive. I think the name is positive.
Okay.
Average positive, yeah, AVG positive.
Of those matrices.
Of those matrices. So what is this? The average delay, then you get the average delay. And then close it. Yeah. So okay, so this is the same unit as in the matrix. So N positive, N underscore average AVG positive of travel time. So then you go to travel time. Okay, so the same thing with N underscore average positive, okay, of the speed. The speed, right? Good. So the average speed is in your case 20 kilometers per hour. Okay. So now in transport, usually we want what is called a vehicle time and vehicle distance. And then you will have vehicle speed. How do you know how to calculate that? Okay. Vehicle time and then vehicle distance and vehicle speed, right? So in this case, you multiply, vehicle time, okay? You multiply the flow. So element-wise multiplication. Okay, you multiply the flow with the travel time. Okay, vehicle distance, you multiply the flow with distance. This is element-wise multiplication, so scalar. I don't know if in your version you have Hartman product. N underscore, it's
Just division.
No, also didn't. Okay, so then you just multiply. You just put some products.
Some product
Yes. As
of the flow matrix.
of the flow matrix,
And
the blue one. Okay. And then with the, what is this?
distance, vehicle distance
So with the L.
with L.
Yeah. Okay. So and then vehicle time, the same. The flow matrix, some products of the flow matrix with the travel time, T. I think, yeah. Okay.
And
Be careful with the units. Now, vehicle speed is easy. Vehicle V is equal to S per T, right? So vehicle distance divided by vehicle time. Vehicle distance,
okay. So that's just it.
yeah.
Distance over time.
Yes,
And
that's
since
it.
we are in minutes,
Then, yeah, and then you need to change that.
multiply it by 6.
Be careful with the units.
Yeah. You need to multiply by 60. Here.
Very small. 14.
11.4
Okay, so 11.
vehicle kph.
So that is the performance indices that you can use. Huh? So I have another proposal for you to check whether your indices is actually closer to the ideal condition. So I call this FAR P index. So you can have another there, FAR P, FAR pi. So N underscore
What is this? N underscore.
N underscore FAR pi V V VA
Var pi.
FAR pi there.
Okay.
So you can go to the in the lanes or capacity by lanes or capacity per hours. This same.
This.
Okay, that one is okay. Close it. So okay, then you can put that at percentage. So your network is about 39% of the ideals. ARPA index. So the closer your FARPA index to 100%, that means your network structure is more robust, okay, and more difficult to. Basically, you will have less congestion in the entire network. Okay. You can try that. Okay.
Sure.
Okay.
Okay.
Okay. So you get everything under your control.
So the idea, sir, is to make it close to 100. The
Very difficult to make it 100. And what you need to do is comparing base scenario and alternative scenario, whether your alternative scenario is actually better,
in
closer
terms
to
of this
the
one.
condition or not. Yes.
Okay. Okay, I'll do the alternative, sir, and then show it again.
Yeah, okay, good.
Okay. Thank you.
Thank you. So how about the others? Did you get lost? Or do you understand or you don't? Tell me, give me feedback so that I will know what you understand. Anyone have? You have some feedback? Did you get it or you don't? You're able to make up to congestion?
Sir,
Yes.
I tried following your instructions earlier, but um I just finished up to capacity and then I was not able to follow when you were
Okay,
discussing with
let's you share your screen, I can help you. No problem.
I just got up to this point, sir.
Okay, so this is the capacity and then you multiply.
Yes, sir. With the
This is the scaling capacity.
yes.
Okay, good. So now you can create new matrix called flow. So just delete everything on that side. Yeah, and then change it to flow. Okay. So now in your no, in the flow you just put underscore equal and n underscore. Okay, so capacity to you just type C. Yeah, capacity to ideal flow. That one. Right. So tap. Okay, and then you put the capacity. Oh, not yet. You did not close yet. Wait. And then comma. Available. Capacity. Capacity to ideal flow. And you get the capacity. Yeah, you tap. You get the capacity. Comma. Your total flow. Okay, close it. Close parenthesis. And then enter. So then you hold shift button. Oops, only 5. Okay, going down. Okay, and then click edit or F2, and then shift control enter together. Shift control, yeah. Okay. So then you can check this is pretty much it or not. You get the sum of row, sum of column. Sum above. Oops, only 5. So yeah, this is pretty much it. You see the button is the same, right? Okay, and then you can check the sum of total for things then. This is supposed to be 2,125. Yeah, okay. So you got so now you create a new matrix called congestion. So maybe congestion. So remember congestion. Congestion is what do you call that? Unitless, no units. Okay, that means the unit of capacity in here must be PCU per hour, right? Because you multiply. So this P, you type the unit, yeah? And then the flow is also PCU per hour. But this total flow is PCU per hour, not per lane. Yes, that one is PCU per hour. Okay, so then this P must be PCU per hour, isn't it? This one is PCU per hour. This one also PCU per hour, right? So then this one is just Hadamard division. So you just delete the thing. N underscore. It's Hadamard, the name of the person. Yeah, that one. Hadamard division of a flow matrix, comma, capacity matrix. Okay, close. Okay. Because this is an, oh, okay, you delete first before you type, because you already have a matrix there. Delete that there. Okay. Then again, Hadamard division, N underscore. Yes, the start of the flow matrix and capacity matrix and close it. Okay, and again you highlight, you select all the size of them. No, did not do that yet. Don't copy, yeah. Going down, you just save, you hold the shift button and then use arrow to the left and to the right, bottom and the right, and then edit here, edit here, and then shift control and then enter together. Yeah, okay.
Sir, every time we use the formula N underscore, we should always do the shift control, right?
No, in the N underscore, there are two. Okay? One is scalar, the other one is array. So array formula, okay, is not depends on me, that depends on Excel. So for example, if you do matrix multiplication, matrix inverse in Excel using the Excel, you also use the same technique, which is highlighted all, okay, and then shift control enter. That's the technique of Excel, not me. Okay, so check in the manual of IFN Excel add-ins, okay, whether this is scalar or array. If this is array, yes, you need to highlight and then shift control enter. So if this is scalar, you don't need. Okay, so wow, this is interesting. You got oh, very much. You, how did you get this value?
Actually, this is the total flow we computed for our paper.
Hmm.
That's why
Yeah.
I'm trying to do it using this one.
Yeah, this is fine. So this is interesting. This is what we call as premagic equilibrium. Okay. Yeah, you got something interesting. Huh? So premagic equilibrium means the congestion is a steady matrix. That means all the congestion become all the same, the positive values. This will only happen when your capacity matrix is actually premagic. So you can put it here equal N underscore. Yeah. So N underscore is premagic. Is 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 premagic. There is premagic of this one. You try this. The whole matrix must be true. See, so when your capacity is pre-magic, yeah, in terms of number of lane or in terms of PCU, yeah, then you will get the best matrix, yeah, the best congestion, which is pre-magic equilibrium. Yeah, this is the ideal condition. If you calculate the far pi of this, it will be 100%. You can try. The performance, okay, so equal n underscore v var pi va there of this matrix. You will get 100%. See, 100%. So you get the ideal condition of an entire network. Yeah. Wind, such as a while ago, get like 40%, right? So you get 100%.
What does that mean in the actual transportation?
So in the actual road network, if you can make your capacity like this, then you reach the ideal condition. This one, you see the congestion is very low. Okay. If you want to make a new town, a new city, you design it this way. As an architect, as an urban planner, you design it this way. Okay. But if you are having the old town, okay, like Metro Manila or whatever city, of course, they will not reach 100%, right? So because you don't design it. So they grow over time, isn't it? So when they grow over time, then you can start to check the far pi index. Okay, how many percent they are. And then you want to change, okay? You want to change the number of lanes and so on, so that closer to this 100%. But very expensive, of course, to change the number of lanes to be 100%. Okay.
Sir, I have an additional question.
Oh, cool.
What if this is the closest value that we can get based on the data that is available, but then if we observe the road network, it does not seem to reflect the ideal flow that that you were mentioning.
The road network.
So there's yes.
This one?
No, sir. I mean in the actual condition.
The actual one, so you need to get the real matrix and then calculate this. What is the actual lane capacity matrix? And you can get this one and congestion. You can go, wait. I think I have the matrix, right? Wait, yeah, I will find the link for you. There. Okay, let's do this. I will send you in the chat to all. Yeah, you can go to that site. So instead of using Excel, you can also directly use this traffic assignment in matrix version. So, okay. So if you don't like Excel, you can use that matrix version. It's the same thing. Yeah. I don't know. So in Excel, you have more power to do what you want. So in that site, of course, you are limited by the program. And so here you can change on your own. But of course, more work. Okay. So, for example, in here, FarPy, you cannot get there in the IFN Transport matrix, but you can do it in Excel. I hope you understand the meaning of pre-magic equilibrium. So PLAN is having a very good example here. Okay. So when your capacity is already pre-magic, okay, then your congestion will become steady. This is the best in the entire network, any network. This is the ideal condition. Okay. So then you can check the real network, how much. Okay. How much is it right now compared to the ideal condition. So if you can compare that, then you will say, okay, so how many percent? So what is FarPy? FarPy is a very simple index. Okay. Which is based on average of congestion minus the maximum, maximum congestion. Okay. The average congestion compared to the maximum congestion, then you will get that. I will show you the slide. What can I share? Okay. Let me go to the slide. Yeah, we have discussed this time about this. This slide is in model. Okay? So basically, IFN is just a graph. We already discussed about random network, so I just skip this part. Okay. Random walk we already discussed. Right, so this is the code. So we already discussed. Oh, this is how you compute the strongly connected network. Yeah? Is this network strongly connected or not? Is this network strongly connected or not? Huh? Anyone can say whether this network is strongly connected or not? Strongly connected means from any node, I can go to any other node. Yeah, from A, I can go to B, to C, D, E, and F, no problem. But can I go home? Oh, from A, I cannot go home to A, right? So this is not strongly connected. Yeah. Yes. So A, B, C, D. ABC is basically the component. ABC is the component. Okay. So and then E and F is also another component. D is not included. Oh, C. EF is the component. Yeah. So this is the source and this is the sink. D is not included. So in this case, this is not strongly connected. Yeah, this is actually weakly connected because it has absorbing class of EF. Once enter the EF, cannot go out from this absorbing class, absorbing component. So now, how I will know? In Excel, there is a n underscore is irreducible, right? So how I get that computation? Yeah, that actually depends on this formula. Yeah. So this is the formula that we use. Now this is the linear algebra formula that I use to check whether this matrix A is actually irreducible or not. So if this passed the test, meaning it's primitive, yeah, this value I is the identity matrix plus A, n is the number of the size of the matrix minus 1. If this is primitive, meaning all positive, then they are irreducible. Otherwise, it is called reducible. Reducible means either weakly connected or unconnected. Yeah. Weakly connected means you have a source component, okay, source node, sink node, or sink component. Yeah, these are the possibilities. So irreducible is strongly connected, means from any point you can go to any other point and then come back. So using this simple test, okay, let's apply this. We know this is reducible. Yeah? This is not strongly connected. So you will see this is the adjacency matrix, right? Then what you will do, you add with the I. Okay. This has 6 nodes, so then 6 minus 1 is 5. So exponent to the 5, then you will get this value. And you see here, okay, these are not all positive. Yeah, you see a lot of 0 here. You know, if 1 0 exists, then this is not strongly connected. Yeah? So should be all positive. Yeah, this matrix must be all positive. Then this is irreducible or strongly connected. Okay. So this is the same thing. Is this is irreducible or reducible? Strongly connected or not? Any point, can I go to any other point? Yeah, this is strongly connected. Yeah. So if you want to test, not visually, but imagine if your market, if your network very big, so you need to test using computer, right? So in that case, you use matrix. Yeah. So you create the adjacency matrix of this. Okay, and then you use this formula. Yeah. 5 here is the number of nodes minus 1. Oh, you see all positive, yeah? No 0 at all. So in this case, irreducible, yeah? Strongly connected. Okay. Now, if I change this direction, see, this is going there and this is going to the left. If I change this direction, now both going to the left. This is surely not strongly connected, isn't it? So this is the source and these are the sink. Yeah? So, okay. So what happened if I change this matrix into matrix? Yeah? Then you will get, oh, some of them are 0. Yeah? So you will see some of them are 0. That means this is weakly connected or reducible. Yeah. So premagic I already discussed with you last week. So yeah, if your network is actually so network can be divided into 2. Yeah? One is unconnected. So if your network is unconnected, you cannot use IFN in any model. So IFN is not Manasseh. If your network is unconnected, cannot. Okay. If your network is connected, then you have 2 possibilities: weakly connected or strongly connected. Right? If your network is strongly connected, then it's fine. Yeah. If your network is weakly connected, then this must contain at least one of these. Yeah. Either sink node, source node, sink component, or source component. So in that case, you can add the cloud node. How about if my network is already strongly connected? Should I still add cloud node? That is up to you. That cloud node is actually optional. Okay, so you can add cloud node in order to make, even though it's already strongly connected, you can add cloud node, yeah, in order to make it pretty magic. So, okay, yeah. Remember, IFN requires strongly connected network. Okay? If your network is unconnected, you cannot model using IFN. So, but if your model is weakly connected, then you have choice. Okay, look at the size of the network. If the size of the network is very big, the city network is usually very big, then you need to clean, yeah, by reducing. So that's exactly what I'm doing in the IFN transport, isn't it? So I use Target algorithm to get the largest strongly connected component. Okay, or you can connect directly the source node and sink node, or alternatively, maybe better, you add cloud node. Okay. In here, we will add one more node. I call this cloud node. And then indirectly, you connect the source node or component to the sink. Yeah? So you connect the source to the sink through cloud node. Okay. So the cloud node itself is an optional. Yeah, it's a modeling tool. Yeah, to connect the sink to the source. So via dummy link. In the metaphor, easier to understand is cloud, something in the sky. So this represent God. Okay, so dummy links represent your prayer. So if you are weak, okay, weakly connected. So if you are weak as a person, so you need prayer and connect to God, then you will become strong. You see, okay, so that you can easily remember that. Yeah. So to make a strongly connected network from weakly connected. Okay, but you can also use a cloud node to model external environment outside the system. Okay, of course, the cloud node can be hidden later for better visualization. Okay? Otherwise, the dummy link is sometimes quite confusing. So IFN is monotheism, so there is only one cloud node. Yeah, so there is only one God, right? So only one cloud node is sufficient and not necessary to convert the weakly connected network into strongly connected network. Yeah? So again, if you are dealing with a weakly connected network, all you need to do is just connect directly without cloud node or with cloud node to make it strongly connected network. Yeah? Connect directly the sink to the source. Okay, so I will show you by example so that you will understand this. Okay, and then we will calculate the IFN. Okay, so here, this is a simple network. Okay, this is the source. These are the sink, isn't it? Okay, so if you put cloud node, so you create a dummy links here. Okay, and then this is the cloud nodes. Yeah. Once you get the say, of course, this is 1 and 1, this is 2. This is wrong. Huh? This must be 2. I think I made mistake here. So this must be 2. Okay. So with okay, so this is better. Huh? 2. So you can connect directly without cloud node or with cloud node. Yeah. So let's see this one. This is an example of an intersection. Okay, and the numbers here represent the capacity. Okay, if you look at this is already the network itself is already strongly connected, isn't it? But I still add cloud node. Why? Okay, because this is represent one intersection. Okay, but where does traffic come from? They are not just turning around here. Okay, they must come from outside of the system. So the cloud node here represent the external environment outside of our system. Yeah. So they go somewhere else and then they come from somewhere else also. So that's the cloud node here represent the external environment outside of our system. Okay, so this is the modeling tool. So let's practice this. How do you add the cloud node? So identify the source, yeah, and this is the sink. So this is very typical waving section. Yeah, in the roundabout rotonda, yeah, you always have this one is traffic going straight and then going to the other direction, and there is a waving section here. That now you want to know how many, right? So in this case, you can just create a cloud node, okay, to connect. Easy or not? Yeah. So let's practice this so that you will understand the meaning, okay, of IFN. Yeah? So here is the typical very simple intersection. Only one way from left to right, and then from north to south, yeah, from the top to bottom. And what we know is only 4 numbers, yeah, TRSU. So from A to E, I know 100, right? And then from B to E, where is this? This one, yeah. B to E is 200, I know. And then from E to C, I know 50. And then from E to D. So all the link flow I know. Yeah. I know the link flow from this value. I know AE, BE, EC, and then ED. Oh, if you know the link flow, can you get the turning movement T, R, U, and S? Can you get? So my question to you, is this flow matrix pre-magic or not? Some, of course, this is not pre-magic. Now the sum is 100 here, 200 here, and this is 0, you see. So this is not, and again, this is 0. So this is not pre-magic, huh? Okay. So yes, this is not pre-magic. So can you make this into IFN? What you will do if you want to make it into IFN, you will add cloud node and then dummy links. Okay, can you practice this? This is very simple, okay, but you will see the power. Okay, can you practice this? Just type. So all you need to do, yeah, you just copy everything. Okay, just 4 numbers here. Type in Excel. Okay, and then you add one more column, Z, for example, and then one more row here, Z. Okay, and then of course, what you will do, if E to C, what is E to C? E to C is 50, then going to the cloud node is also 50, isn't it? So Z from C to Z also 50. Yeah. So how much is PE? PE is 200. Yeah. So PE is 200. So from the cloud node to P is also 200, right? So we continue. The same thing, yeah. A to E, how much? 100. Yeah. So in that case, from the cloud node to A is also 100. Same thing here from E to D. E to D is 250. So then from D to Z, cloud node, is also 250. And just continue. Okay. then suddenly you will start to see, okay, wow, this become IFN. Yeah, now you start to see this suddenly become IFN. Yeah? So initially the F is not premagic, okay? Not even strongly connected, right? But once you connect it to the Z, to the cloud node, okay, so you just continue this value, right? Suddenly you will get IFN. So what is this? This is the hidden value in the system, okay, that probably did not show in the usual flow matrix. Yeah? But once you develop the IFN, then you can refill everything. So please practice this and the intersection and waving section so that you can start to understand the power of the cloud node. So once you have this F, which is already pretty much irreducible, so IFN, so can you calculate the T, R, U, and S? Okay, so you can calculate the value of T, the turning movement. Yeah? What is T here? Is BEC. From B to E, and then from E to C. So that must be 50. Okay, so any question? Do you still try to grasp this or? Okay. You can also practice this one, yeah? So this is the T intersection. Look at this. This is already strongly connected, yeah? But if you look at this is the flow matrix, which is not premagic. Okay? Yeah, this is strongly connected, irreducible, but not premagic. So this is not IFN, right? So once you make it IFN, okay, how? You just add cloud node. So once you add a cloud node, yeah, then it suddenly become IFN. Exactly. Okay. So this is the power of IFN. Yeah? So you can start to see the hidden structure behind the scene. Yeah. And of course, from here you can get the turning movement. From A to B to D, how much? So A to B is 1,000, and then B to D is 750. So in that case, the minimum between the two is 750. So A to B to D is 750. Okay. How much is the turning movement from D to A? From D to A. So D to B is 600, and then B to A is 150. So in that case, turning movement is 150. The minimum bit. If you only use this, you cannot get. You cannot get the actual turning movement because this is not IFN. In fact, this is what happened a long time ago when I was still undergrad. I do counting on the floor, on the street, right? So we get all these numbers. Of course, they are not matching with this. And what happened is I want to get the turning movement. Yeah, I cannot get. Yeah, because we are missing a lot of numbers. Yeah, but once you make it into an N, suddenly you have a lot of information, hidden information revealed. Similarly, this is also another waving section. Again, in this example, you don't have not pragmatic because not even strongly connected. Okay? But once you make it with the cloud node and dummy links, yeah, so suddenly you can start to see this is actually strongly connected and pragmatic. Okay? Okay, up to here, is there any question? Any question? Or you give me feedback so that I will know what do you understand or what you don't understand. What is the name of the PDF? Can we assume any value? No, you cannot assume any value of for the Z. Yeah, the Z must be continuous from the value with the end of the node. Yeah, which is the sink or the source. The name of the PDF. The policy analysis. I think the name of PDF is policy analysis, isn't it? Mhm. Oh, you don't have that. Yeah. Okay, so in that case, I can upload. Okay, so I will put IFN2. Wait a minute. So in the moment, can you just try this? Well, okay. So in the moment, you can just try to do this. Okay, can you try this, for example, or this one? Maybe the easiest is this one. Yeah. Can you try this T intersection? Then I will upload to on this one uploaded. I thought I already did. One. Okay, so can you refresh your browser? And I just uploaded the IFN2 in model slide so that you can use that also. Okay. Thank you, Mark, for the feedback. Yeah, it's uploaded. The name is IFN2. Okay. Just refresh your browser and then you can download it. So one thing, yeah, this is not in the slide, but there is actually deeper deeper meaning than that. Yeah. So uh, I'll just show for a while. This is not part of the example, but I just show you. So we can actually do something like this. Yeah, if this is your nodes, right? This is the nodes. So you can also create links. Yeah, you can also create links versus links in the matrix. So this is called line diagram. You see this? What is this? You have A, B. So yeah, you have B, C. Put here. Then you have B, D, and then you have in here D, A. Yeah. So order doesn't really matter. So you just keep your own order. Okay. Then you will have line diagram is basically link to link. Yeah? This is node to node. This is link to link. So here you will get the turning movement. Okay. Now you are dealing with 3 nodes. Okay. The interesting part of this is the same. Another example. Okay. This is an example of just flow matrix 3 by 3. Okay. Then you will get the values. Yeah. So in here I have 4, 1, 3, 3. Yeah. So I just cross it per row, per columns. Yeah. So 4, 1, 2. And then if you sum, of course, 4 plus 1 plus 3 plus 3 is 11, right? Now, if I use the path matrix, which is link by link, so the graph. So look at this. This number, okay, which I already make it this way. So it will become the sum of the flow. Okay, this will become the, and this is always Pragmatic again. Once your flow matrix is Pragmatic, okay, link to links is also Pragmatic, and then the sum of row and the sum of column is actually from the previous one. Okay, and then you can create a new one. Okay, 1, 3, 1, 3, 3. So I can create a new one. The sum is always the same. Okay, then you can also get this one is 2 nodes, right? So you will have B, A, B. Yeah, B, A, C. Can you see the default here? Okay. A and A. Yeah? So you can also get now become 4 nodes. Yeah, you can have 4 nodes. But interestingly, look at this. This one is the pattern that you have here. 1, 3, 1, 3, 3. 1, 3, 1, 3, 3. This is exactly the same as the sum now. The sum of row and the sum of columns. Yeah. So you can continue this way. Yeah? Of course, there are many possibilities. Yeah. In here, you can have many possibilities. So the point is, you can continue the path. Yeah. So of course, check on the graph. Okay, and this value is come from the actual graph. Okay. The point is, once you have ideal flow matrix, okay, when you go to turning movement, again it will become ideal flow matrix. Yeah, and then you go to the path, 3 nodes, 4 nodes, and so on. Again, it's all become IFN again. Yeah, so it's a closed system. Mathematically very interesting. Yeah, any question so far? So from here, okay, this is the T intersection, okay, and these are the flows given, link flow, A, B, B, A, and so on. So if you have the link flow, you can add cloud node, okay, and then these are just continuum, you see, yeah. So going to A, B, is 1,000, isn't it? So in that case, from the Z to AB, yeah, ZA must be 1,000. Just continue the flow. So the same thing with the waving section here. Yeah, so this one I know only the link flow. You can conduct survey to get this link flow, right? My question, if you know this link flow, I want to know how many from E to D, how many from A to F, right? That's exactly what you want to know. So this alone will not give you the value. But once you get the IFN, yes, you can get the value. Yeah. Why you can get the value? Because the next IFN, the next nodes, two nodes, three nodes, four nodes is again IFN. Yes, Jopen, you want to ask me?
Sir, is there only one answer for the exercise a while ago?
Oh, which exercise?
The T section, sir.
The T. This one?
Yes, sir. I got different answers, sir.
Oh, you want to show? Okay. I will stop sharing.
I'll just share my screen, sir.
Yes. Um,
I remember, sir, to be it IFN should be pre-magic, right, sir?
the IFN must be pre-magic, that's correct.
So, here's my trial, sir. Can you see my screen, sir?
Yeah, I can see your screen. So you have from A, B, D. Oh, how about A to Z? From A to Z, you did not add.
A to Z, sir.
A,
It's already 1,000. I got same sum, sir. It's not valid, sir. I did not change anything from row A.
you know what's the problem here? You created the C to Z, right?
Yes, sir.
Yeah, so this one, but you did not get from Z to C. So where this come from? From C to B, where this flow come from? That means they are only turning. So this is only turning like this. Or actually from the Z coming like that.
So if I add from add this,
The same thing, yeah. This one you have A to B, isn't it? Right? So yes, you have from Z to A, that is from outside, go to A and then go to B. Yeah. But how about this one? B to A. Where it goes, is it just turning back here? Or actually going outside?
It's just turning back because there's no way I can.
So that is a problem. The same thing in here. So this should be some from Z to D, isn't it? Otherwise, this will turn just back.
So if I add a cloud node, sir, I should be returning it back to the starting node.
The cloud node is just optional tool to help you, right? But that represents the external environment, isn't it? But without that dummy link that you provide, that means from B to A, it will come back to B.
Yes, sir.
But that's not true also because B to A is already how much? 150. And then A to B is 1,000. So that means out of this 1,000, 150 is from B to A, which you don't intend it that way, isn't it?
Yes, sir.
So in that case, you need to add the the connection to cloud node. Otherwise, the intention will be different.
Okay, sir.
Again,
Do it, sir.
this is just a modern tool, but you understand the meaning,
Okay, sir.
not mechanic only.
Okay, sir.
Okay.
Thank you, sir.
So I hope this is clear. Yeah. Thank you for the good question. Okay. So how about the others? Is it clear or not clear? Yeah. So correct. So you need to be consistent. Yeah. The flow must be consistent. Yeah. You cannot just assume any values for the Z. That's correct. Correct. Yeah. And adding cloud node is just extending the link. Yes. To the external source. That's correct. Okay. And then we hold the flow balance in this node. That's correct. So you need to make it pragmatic. Okay. Otherwise, the meaning will be different. But remember, yeah, once you make it into a IFN, yeah, pragmatic and irreducible, okay, strongly connected and balanced, then you can get the turning movement. Okay. Without that, you cannot. In fact, you can get all the paths, yeah, up to how many nodes, it's up to you. You just keep making the next IFN. Okay. I understand this is a little bit pushing, yeah, to you because like long research and then you put it into just a few minutes. But at the same time, probably if you try to watch this video again later, okay, then practice, and then you start to realize the power of IFN. Yes, we are not just making some equal, eh? Correct. So you need to have some notes also filled in based on the continuation of the flow. Check the meaning, right? So there is no isolated on disconnected part. Okay? The Z is not unconnected. Yeah, the Z itself must be the Z itself must be the tools to make it balance. Cloud node is very important modeling tool, even though it is optional. Yeah, but this is a very important modeling tool. In fact, when you want to use, well, if you want to apply IFN, not for transportation, but for other field, cloud node is very crucial because this is the one that we can create a cycle. IFN can be created by cycle. So from the cloud node, for example, I want to apply this for text processing. Okay, so all the word become one node. Okay, and then each sentence which start from cloud node, and then the first word, the second word until the point, the period on punctuation, okay, and then come back to the cloud node. Yeah? So that one cycle. Then we create IFN from the word. The same if when I try to make this into music, for example, yeah, it's note in the music, so become one note, okay? And then we connect one bar from one cycle. So then you need cloud node again. I hope this is clear. Once you practice this, then you start to understand. Oh, you see here, this is this matrix, yeah, is strongly connected, but not pragmatic, isn't it? Okay. This F on the top is strongly connected, but not pragmatic. Yeah. So then, of course, this is not IFN, not pragmatic. So the bottom here is the one pragmatic and irreducible, yeah, strongly connected and pragmatic. So this is the IFN. So once you make it IFN, then you can continue all the analysis. Oh, the screen is not share. What should do? This one. Yeah, the top view here is not pragmatic. So this one is just strongly connected, but not pragmatic. So when you add the cloud node, suddenly it becomes okay. Of course, you need to fill up the term meanings. Then you can have this is done correctly. Yeah. If this is correct, it must be pragmatic and strongly connected. If not, then something is wrong with the computation. In fact, that pragmatic is becoming my test, whether my computation is correct or not. Okay. Is this clear? I hope you can practice this and also this one. This one is same. Yeah? So once you add the cloud node, and this is the value, then you can start to see that this is pretty much awesome. Okay. Is it clear or not? This is clear, so I will continue with the next topic, with this calibration. Right? So are you okay? You need some time to practice. Okay, so let's go to yeah, a few interesting part. Yeah. So ideal flow is a relative flow. That means they are a rational number. Yeah. You remember when we discussed random walk? Okay, so flow itself in the random walk will just go to infinity. Then so it doesn't, it's practically useless. But when you divide the flow with the statistic of the flow, yeah, either sum, average, standard deviation, or minimum, maximum, and so on. So you will get relative flow. So because this is a relative flow, so of course something divided by something, right? So numerator divided by denominator. So this is rational number. Yeah. So once you have the rational number, okay, you can scale it up and scale it down. So I can multiply, yeah, any value to create equivalent IFN. Yeah. Okay, so when the total flow is 1, then we call it basis network. Yeah, why? Because this represents the probability, yeah, link probability. Okay, so this is the definition of equivalent. Suppose you have two networks, N1 and N2, both are ideal flow network. Okay, so then we can say that two IFNs are called equivalent if and only if, and there is its corresponding link flow is just multiple of the other by positive scaling, global scaling. Okay, so we said this is the symbol of equivalent. That means you can multiply by a positive number. Okay, so when we have the minimum integer flow in all links, then we call this cardinal network. Yeah. So to make it easy to remember, you just remember cardinal likes integer. Yeah. So several interesting properties of equivalent IFN. So of course, when they are equivalent, that means they have the same stochastic matrix. Okay, and they also have the coefficient of variation of the flow are also the same. Yeah, and then the average node entropy is also the same. The relative flow is equal to 0. Okay, so these are the four standard form of equivalent IFN. Okay, when the total flow is 1, we call this basis network. Yeah? So when the minimum flow is 1, then we call this unit minimum flow. Okay? When the maximum flow is 1, we call this unit max. And when all flow are integer, which is minimum, then we call this cardinal network. Yeah? This can be done by FCM. Last time we already practiced this. Okay, so this is an example. So suppose this is your IFN using a simple integer number. So this is cardinal network. So the total flow is 38, right? So now you know that total flow is supposed to be 17,500. So in that case, how to get that? Easy. You just find the scaling. Yeah, the scaling is what you want, the target, 17,500 divided by the actual kappa here, which is 38. So I got the new scaling, this value here, which is 460.5. So then this one I multiply for each of this value with 460.5. Yeah. So then the total will be exactly 17,500. Okay. So the same thing. So this is in the basis network. So the total here is 1, right? So in that case, you put it into fraction and then you look at the denominator. Yeah. The denominator, you get the LCM, and here is only 1, so 49. So when you multiply this with 49, then you will get this value. Yeah? Of course, the total now becomes 49. Yeah? Okay. So from the basis network, okay, which total is 1, okay, if you multiply by the LCM, you can always scale it into integer. So these are the cardinal network. Okay. So yeah. From here, if you want to get the cardinal network, what you will do? What is the scaling? Yeah, yeah, multiply by 2. Yeah, correct. So, so if you multiply by 2, okay, you will get this value. Okay. Remember, cardinal network, the minimum not necessarily 1. Yeah, can be 1, can be other number. So in this case, the minimum is 2. Okay. So next, can you identify the basis network and the cardinal network? And what is the scaling from the basis network? Clearly, the basis network means the sum is 1, so this must be the basis network. Cardinal network is the minimum, so this must be the cardinal network. Yeah? Because these 4 network are equivalent, so they just multiplied by some positive scaling. Yeah. From there, from this cardinal network, I can multiply by 2. And here I multiply by 18. Yeah, by 18. Yeah. So here I multiply by 2, and here I multiply by 3. From here I multiply by 3. Okay, so in that case, 18 times 2 and 18 times 3. Yeah. If you want to find the scaling from basis number. Okay, yeah, so this is another just simple. No. Look at this, the cloud and dummy links are there, but I just hide so that you don't need to see the dummy links and the cloud node. But this is already IFN. And so again, you just look at the values, and then you can start to which one is the cardinal network. Should be this one, right? And then to go from here, you just divide by 3, you divide by 2, and from there to there is multiplied by 500. Yeah. Okay, so remember equal stochastic matrix mean they are actually represent the same phenomena. Okay, and the same thing with the flow. Yeah, if you just calculate the average flow, they are different. If you calculate the standard deviation, they are also different. But when you divide the standard deviation per flow, they are exactly the same. Yeah. So here is the example. I have the average flow, they are different. Okay. These are the same network, equivalent. So, and then standard deviation also different. But once you create a coefficient of variation, which is the standard deviation divided by average, you will see exactly all the same. Yeah? This is interesting phenomenon. Okay, so the IFN computation we already did last meeting. Okay, so let's go directly to the calibration. Okay, so now suppose, yeah, you know some link flow, some data. You collect data from the actual flow. Okay, so this is, I call this flow, okay, for link K in the world. So W means world. Yeah, so this is the real world. Okay, so if you observe the link flow from the real world, so that's means the data. Okay, and then this F with the Greek character here, this represents the scaling. Yeah, so this is a model with the global scaling C here. Okay, so this is the model global scaling C. So how to calibrate? Of course, you for the same link K, okay, you minus and then you square it, okay, and then you sum for all the data that you have. Okay, the one that no data you don't need to care. The one that you have the data, that is the one that you have. Yeah? So R here is K1 to R. R here is the number of data that you have. Okay, then you will get what is the result? Global scaling. Yeah? So what you want to know is actually the global scaling. How much should I calibrate in order to match between model and the observer? Yeah. So remember, your real world data represent the ground truth. Okay? Data is the ground truth. Okay? The model need to be adjusted to be similar to the real world. Okay? But be careful, sometimes the real world is also wrong. But using IFN, you can check, yeah, if wrong or not. Let's see, yeah. So when we said IFN calibration, okay, so what we have, we only match the link with the observed data. Yeah, link with the observed data will be automatically calibrated. Yeah, based on the inference of the link flow. Yeah, so we just use the global scale. So let's take example. Okay, I have an IFN already here, so that you can see. Okay, so I already have the IFN, and I want after I observe the flow on link CD, this one, this link CD, okay, apparently it was 900. What is the global scaling? Easy, right? So 900 divided by 3. Okay, that is 300. Yeah? So in that case, I add 300. 900 divided by 3, I got 300. So then I multiply, yeah, this to the this network one by one. Yeah. So now 300 become 900. It's not exactly 100%. Correct. No error. Yeah. If you have only one data, no error. After here, is it clear or not? So you will have start to have problem when your number of data is getting larger and larger. So in that case, we can use R squared. Yeah. So this is called as SE. Okay. This is called as SE. Okay. So sum square of error. This is the one that we want to minimize. So this is the model minus the real world. You square it and then you sum. Okay. This represents the error between the model and the real. Now, you can also calculate what is called as ST. Yeah. So what is SST? So based on your real world, remember the real world represents the ground truth. So okay, your real world data F in link A, then you minus with the average, yeah, the average of that real world data again, and then you square it, and then of course you sum, then we can get SST. So 1 minus SSE per SST, that will be the R square. Yeah? So then what you will do, you will find the global scaling, yeah, see here, in order to maximize. Yeah? This time you don't minimize, you maximize. The physical region must be positive, isn't it? R square, this is square. So this must be positive. But what happens is when your error, okay, is higher than the average, and this is some square total, this is represent the average, error deviation to the average. Yeah? Your error is actually higher than the average, some square total, then the R square become negative. Yeah? That means the amount of error is larger than the average data. So what's that mean? There are some conflict, yeah, between your data and the model. Okay. So when your R square is negative, then you start to understand, maybe my data not represent the ground truth. Okay. So let's start to combine. Okay. I have two data now. A while ago, this is the IFN a while ago. Okay. A while ago, we know that CD is 900. Okay. Remember CD is this one. Okay. So this is 900. A while ago, we get 300 as our scaling, right? Now we have BC is 500. Yeah. BC is 500. Okay. So can we, oh, if you have this one, 300, 900 divided by 3 is 300, right? But 500 divided by 1 is 500, so it's not the same scaling. So what is the global scaling to match the model? Okay. So then initially, okay. So we have the 500, this is observed, and 900 as observed, right? The cardinal here is 1 and 3. So here I have 2, 1, 2. PC, oh, sorry, PC is this one. PC is 2. Okay. So PC is 500. So I have 2 and 3. Okay. So if we divide, we get the 2 scaling, yeah? Not the same. 300 and 250. So let's take the average to 75, right? Okay. So And then let's take the average of the observation. It is 500 and 900. You get 700. Yeah. Okay. And then at global scaling of 275, okay, BC now become 550. Okay, the error is now 50. Right? At global scaling 275, for CD, I got 825. Okay? Then the error is minus 75. Okay? If you calculate the sum square of error, I get this value. Yeah. Remember, this is need to be squared because these are the positive and negative. So you need to square it and then sum. So I get this value. Okay. And then what happened? Sum square of total. Okay. This is the observed. This is the average. Yeah. This is the observed. This is the average. Again, use minus and then square. You get 80,000. Yeah. So then from here you get R squared. Okay. 1 minus this value. So you get 89%. Right. So yeah. This is actually not optimum. Okay. How to get the optimum value? Okay. The optimum value you can calculate using Excel. Yeah. The optimum value is actually not 275 but 285. Yeah. This is the lower SSE and higher R square. Yeah. 91% instead of 89%. How do you get that? Yeah. Easy. Okay, so you start from 275 here, okay, and then you add minus and add, yeah, of the scaling. Okay, and then you calculate, yeah, all the possible values, yeah, the R square and the SSE, and then of course you get the minimum. Yeah. Minimum of SSE is not necessarily the same as maximum of R square, not necessary. In this example, only they are the same, but in general, they are not the same. So you need to stick in one criteria. So say I use maximum R square, then I get 281. Okay? And 85, 285, this one. This is the scaling that we use. Yeah? So once you have that scaling that you have as optimum, okay, then you multiply from the Cartan network to these values. Then you will have this is the final result. Okay. So IFN Transport already give you this one, okay, automatically. Optimum. So up to here is the example clear or not? How you calibrate and get the optimization of the scaling parameter. Any question? So I have data. Okay. If you have only one data, that's easy. R square is always one because no error, right? But if you have more than one data, the more data that you have, usually the R square start to degrade. And here I have 900 and 500. Okay? Then you will get 191%. Yeah, so this is the result. Yeah, this is the result. So you search, yeah, which one is the optimum global scaling in order to find the best based on data. This is practically the idea is to match the data, the model to the data, yeah, on average. Okay. By changing the parameter. What's the parameter? Scaling. Is this clear, the idea or not? So now we can check also if there is a data that is inconsistent, yeah, with the model. I will show you. This is an example. Okay, you have this is the IFN, right? The cardinal. And then we have AB. This one is 450. BC is 600. And then CD is 900. Can you see if this is 900, this is about 300 scaling, and this is 600, again, 600 divided by 2 is about 200 scaling. But this one is 450, this one becomes 150 scaling. Yeah? But one is actually not consistent. Okay? So is this data valid or not for the network? Okay? So we can check. In this example, the average is 650. You calculate SSD, okay? And then apparently this one, yeah. Look at the observe and the IFN. Yeah? So this is 450, 3, right? 900, 2. So this one is going up 2 times, but this is going down. Can you see that? Okay. So this one from here to here this is the same. So this is 3 and 3. But from here, this is actually inconsistent. Okay, so there is a wrong order between the observe and the basis IFN. So in this case, no matter what scaling you use, it will always give you a negative square. Yeah. So let's prove this in the matrix so that you can see. Okay. Suppose this is 450 and this is 900 and 600. Okay, as your input, right? So the block cells are all 0, so I don't need to show. So the yellow cells are the data. Yeah, these are the data that given. Okay. So and the orange cell is something that we don't know. Okay, so let's keep the name because we don't know. Let's keep the name U, V, W, X, and Y. Okay. Then check here. Yeah? This should be pre-matching, right? But this is not pre-matching. You see that 450 plus U, this one, right? And this must be W. So 450 plus U must be W. Okay. And then the second one is 450. But this one is 900 plus V. V cannot be negative. But this is already 450. So V cannot be negative. So in this case, data is not correct. Okay. So you can check, the data is invalid because they do not satisfy the pre-matching constraint. Okay. How can 900 plus something become 450? That's not possible. Yeah. Something must be positive, right? The V must be. So in this case, you can start to see the same thing here. Right? The third column, this is 600, but this is already 900 plus Y. So Y cannot be negative. So it is again twice inconsistent. So the data is inconsistent. Okay? Even though we consider data must be ground truth, but sometimes the survey is not correct. So we can check. Using IFN, we can check if the data is correct. Okay? So there is a conflict. Okay? Okay. So in that case, oh, maybe this is not correct. So maybe 900 must be 400. Okay, so can be. Yeah? So if you corrected that, you will get pre-matching. Yeah? But again, that correction should be consistent and also check back in the field. Yeah. So up to here, is there any question? So you know how to calibrate IFN using real data. Any question? Any question? Anything to discuss? So, I will show you in brief a few example of policy, and then you will present your work. Share. So you can add and remove one link. So as a dynamic network. So the question is, of course, in this simple example, we assume something. So all link must be equal capacity. So in that case, the flow is identical to congestion. Okay. Then we can do a simulation. Yeah. What if analysis? What is the effect of adding a link to the congestion to the network? Yeah. will add links actually reduce congestion or increase congestion? Yeah. And which link should be added minimally to reduce the maximum congestion? Yeah? So this is the initial network. Can you see? And, we have only 5 nodes and 5 links. Okay, this one. So because all the same, so this must IFN must be 111, right? So and when we add one link here, okay, so this will be add, then of course this we assume this is equal flow. So in this case 1 and 1. So in this case this must be 2, right? So this is continuous, so this must be 2. So look at this, adding one link, okay. So compared to this earlier, so this adding congestion twice. Okay. Now in C here, I add again one more link here. Okay. So what will happen? Adding one link actually increase the congestion again. So you probably will ask, oh, is this true that adding link is actually adding link mean you add a new road, adding link is actually increase the congestion level in the long run, yeah. This is in the long run. So is it true? So well, not necessarily, yeah. So from here, I go here. Again, I add one more link here. But look at this, yeah. Here I add a link here, and then the congestion is near, yeah, before. Yeah? The congestion is before, yeah. But when I add in here, okay, the maximum congestion is actually far away. Yeah? 2 links before, yeah. So yes, up to this point, we will say that adding links actually increase the congestion level, yeah, from 1 now becomes 6 now. From here, what will happen, yeah, if we add different links? No? If from here I go to E, and then from here I go to F. Yeah? So the same network, I just add this link or this link. Yeah. So you will see the maximum congestion now reduced, yeah? From 6 now become 3.5 or 4. So what's the conclusion? It depends on where you are the links. Okay, it's not just adding links randomly. You need to add links based on certain optimization. Okay, so now this is another example, okay, of IFN, cardinal network modeling. So suppose the maximum flow in link A, B here is 6, right? So kappa, the total flow is 27. Okay. So then you want to ask, what will be the one link you want to add in this network in order to reduce, yeah, this maximum flow. Okay, but the kappa must be constant. So this is very simple but interesting questions about optimization, right? So you can try one by one. You can search all. This is the base scenario. So you can search what will happen if I add this link. What will happen if I add that link, and so on. Yeah. So the best link to be added is actually in CA. Yeah, this one. And it will actually reduce the congestion by 16%. Yeah. So, and this is another example. Using IFN, you can not only do checking the policy, but you can also predict where and when, where and when that traffic congestion will happen. Okay? If you insist on one a set of policy scenario. Okay? So in this example, I use adding lane, just add lane. That means road widening. Yeah, this is what is many government would like to do. Okay, they always want to widen the road, right? All the house and the offices become road. Yeah? So this policy is simple. So we will add one lane on the most congested link. A while ago we said, oh, if we reduce that, okay, when the maximum congestion reaches 0.9, then that link alone we will add one more link. Okay, there is no change in the network, so this is an assumption. And let's assume the lane capacity is 1,500. Okay, and of course, if you want to know where and when, okay, you need to get trip gen, right? Trip generation. So let's assume this because this is very small example. So city population is initially only 1,200, and the car population initially, 550 cars. Let's start with the year 2000, so because this is 00. Okay, and we know the population growth is 5% per year, and car population growth is 7% per year, higher than the population human. Okay, and we have econometric model, which relate the population at certain time with the total flow in the network. Yeah. This one you can do certain survey, and then you can put it into IFN, then you can create this model easily. This is just simple linear regression, right? So we'll use this model. Okay, what will happen? So initially, this is our network. We know the lane capacity. Okay, so because one lane represents 1,500, so you just multiply. Okay, so this is the in PCU per hour. Okay, and at this point, what is the total flow in the network? This one, the total flow in the network. Yeah. So at the year 2000, okay, you have the population earlier given, right? This one, car population is also given. So then you have the total flow in the network. Yeah. So if you know the total flow in the network, what you will do, and you know the capacity, so what you will do? You will get the maximum congestion. Yeah. So this is the stochastic does not change, right? So this is the flow matrix that you get from this value, okay, to get this value. And then based on the capacity and flow, you can get the congestion. Yeah. So we know in the year 2000, okay, the congestion, maximum congestion is still 0.61. Okay, no problem. That is the base scenario. Then you want to know when and where it will reach 0.9. Okay, so in that case, you project the population. Okay, you project the population and you project the car we know this is 5%, this is 7%. Okay, and then based on this projection, what you will do, you can calculate the total flow, yeah, based on this model. Well, yeah, this one. This is the model, right? So you can calculate the total flow. Okay, so then you will ask when the maximum congestion will reach 0.9. Huh? So this will reach 0.9 when the total flow become 16,200. Where is come from? This one. Okay, you just with the scaling, yeah. 0.9 divided by 0.61 a while ago. Remember the maximum congestion a while ago is 0.61. Okay, we want to know when it will reach 0.9. So I have the scaling factor. Okay, multiply by the total network flow, I get 16,200. Oh, if I know the kappa, then I can get the year. Huh? So here, near here, yeah. So this one is 2009. I will reach about this one. Yeah? In fact, this is the beginning of the year, so you can even get the actual month. You can even know the date. If your model is accurate, you're supposed to get the actual date and month. Yeah? Because 16,200 minus 16,162.85, that is the beginning of the year. Okay, so then you will know remaining. Then you divide by 365, you get the date. Okay, that's how you predict, yeah, the time and the space. From there, oh, I got this 0.9. Okay, the flow increase, okay, at the year of 2009. Okay, then you can continue. Oh, you can continue this. Okay, oh, when will happen? At this point, because in 2009, what you will do, based on the policy, based on the law, okay, that we want to add one link in that most congested DC in this case. So once you add one more lane in that most congested, then that link alone will decrease, yeah, become 0.6. This is what interesting. Once you decrease in one place with this DC, okay, DC become 0.6, but actually congestion spread other place, yeah. So the congestion in other place with this BC and PE now become 0.82. Yeah. Earlier was it's still the same. Yeah. So increase a little bit here. Yeah. So 80 now become 82. Okay. So then okay, 82 is not yet 0.9, so you can still bear. Okay. Then you will ask, when is the next time we need to have adding one more lane and where? Of course, okay, you can predict again. So in this case, 0.9 divided by 0.82, you get the scaling factor. You multiply, you get the same, the new kappa, yeah? The new total flow. So, and then you can check in the table a while ago when it will happen. It will happen in 2011, yeah? This table. Yeah, you can continue this table. Yeah? And so on, yeah? And eventually, you will get something like this. So you will know when it will reach 0.9, okay, and which link we need to intervene, yeah, maximum congestion link. Yeah. And after the construction, adding one more lane, it will reduce. Yeah. And up to certain point in 2027, okay, when you add this, it will become premature already. Okay. So at this point, this is the best scenario that you cannot add just one more lane. If you want to improve, then you need to improve the entire city. So, yeah. So once you reach congested, the most congested, the most ideal, it is pretty much capacity. You cannot just use one policy. You need to upgrade for the entire city with the same policy. So here, another scenario. People always say, I need to add lane to improve the congestion. Is it true? Yeah. So this is actually myth. Okay? Why it is a myth? Because improve the congestion in the lane, actually worsen the congestion in other lane. Okay. So in this case, why it happened? Yeah? Because actually traffic congestion is non-linear. Yeah. So below certain values, 0.8 is almost linear, but after that become non-linear. Okay. So let's prove this myth that lane reduction will actually always make things worse. Okay, so we can prove that reduce the lane can also improve the congestion. Yeah, so this is the example of scenario I put. So let's keep the constant total flow. Okay, and with the capacity per lane is 1.5. Okay, can you observe the lane AC is actually 5 lanes? Okay, and what happened if I reduce? Okay? So using 5 lanes, the maximum congestion now become 85%, yeah, in link city. Okay? And now I improve from 5 lanes, now I make it into 2 lanes, yeah, in here. Okay, so then what happened? Oh, actually better, yeah. From 85 now become 80, yeah. So look at this, from 5 lane to 2 lanes. Okay, the maximum congestion from 85 now become only 80. Yeah, okay, still congested, but we reduce the congestion in the whole network. So this is just to show that IFN can help us to see the interdependencies in the network. Yeah. So you always think that only focus on your project, but you don't think of other links in the system. So IFN help you to see that kind of interdependency. Okay, so we reject the hypothesis that reduction of the number of lanes will always make the congestion more severe. Okay, so the key of solving traffic congestion is actually to find the right policy, the right place. Okay, okay, yeah. So I hope with this you can be useful. Yeah. So now is your time to present your work. Go ahead.
Sir, can our group present first, sir?
Yeah, go. Oh, 5 minutes is okay. Yeah.
I think it's loading, sir.
Yeah. How many groups we have? 2 or 3?
I think 3, sir.
Okay. Okay, you can present. So,
I think my laptop is lagging, sir. Wait.
maybe your groupmate can share screen. If the internet connection is a little bit lagging in your place. Can any of your groupmate can help you, Joben? Yes, June. Yeah, go ahead. Without screen sharing, you can also present. If you want.
I share the screen for them.
Oh, there. Okay.
Can you see the screen?
Yeah.
Good evening, sir. Good evening, classmates. This is our final presentation by group titled Addressing the Impact of Master Plan Development on Traffic, the case of circuit mixed-use development in Makati City. I will not discuss anymore, sir, the first part because this was already discussed during the first presentation.
Okay.
So I will go directly to the methodology. So just a background of the study area was already discussed last meeting. So just the condition of the streets. We just took pictures of the street within the influence of the development. So this is during peak hours. So this is the objective of the study. We already discussed this last meeting. So, but in terms of methodology, we have 8 steps followed during the course of the study. So data gathering, data processing, generation of base scenario, forecasting, identification of traffic management strategy, simulation of future traffic scenario with traffic management intervention, with or without, and a combination of both. And then the conclusion and recommendation. For data requirements, so we collected data on demographics. So this is the projected data of the barangays in Makati City, which include the Carmona, which the study area is located. So based on this, by 2030, the barangay would have a population of 3,016. However, once the circuit development is fully operational, it will pose an additional nighttime population of 41,966 at daytime. Person trips of 103,807, totaling estimated nighttime population of 44,982 for Barangay Carmona alone by 2030. So that's so much
Good job.
huge. of population that will be contributed by that mixed-use development. So in terms of traffic counts, so we required that development to conduct a traffic counts during the start of construction. And this was conducted in 2023, updated to analyze six key road links within the project traffic influence. These are JP Rizal, Kalayaan. So these are the major links within the site development. So based on the result, the traffic counts revealed a total of 40,123 vehicle trips per day. That's across these streets. But the top three types of vehicles reported were cars, which is 28%, motorcycle, 21%, and public utility jeepneys, 20%. So the rest are small truck, taxi, tricycle, motorcycle, bus, and big trucks. Another data that we gathered are the links within the traffic influence. So I just mentioned that the study covered only 1, 2, 3, 4, 5, 6, 7, 8 streets, but we included another 5 as recommended by user last meeting that we have to connect this link. So we just connected this. So we include that 5 more streets. So these are the details of the links. And the projected land use and traffic. So once the development will be fully operationalized, it would generate total of 4 million gross floor area in square meters. So 40% allotted for commercial and 60% for residential. So that's too much traffic attraction and generation that could happen in this area.
Is this number correct?
Yes, sir. This is based on the
Square
development plan
meter,
submitted and approved by the city government of Makati. So for the result and analysis, I will call in Joe Ben to discuss for the base scenario. Joe Ben.
Okay. For the base scenario, so before we perform the network analysis, we model. Yeah. Well, we model the existing network as shown earlier into introduction into 16 nodes and 35 links. This set of nodes and linkage happen to be strongly connected based on the clip version in OSM or the OpenStreetMap. Yeah, you have 35 links, and then as shown there, the diamonds are showing both links, but to and fro.
This one is not model, right?
Not necessary because it is weakly connected to the strongly connected component on the top.
Okay.
Okay. Next. Now we set up the node matrix for it to be loaded in the IFN network. So this is the OpenStreetMap or OSM. So we have the coordinates in longitude and latitude or GPS coordinates. And then just for reference, we put the actual node ID as returned by the OSM feature. So that's the 16 nodes. So next slide, please. Next would be the link matrix. In this one, we use the default immutation on the model. So the suggestion per speed gradient, speed intercept, and then the link capacity based on number of lanes and road width. So this would be your link start node and end node, or and then their capacity and link distances in kilometer, and maximum speed in kilometers per hour. So all the 35 links. So the first 18 on this slide, the last 17 would be on the next slide.
Okay.
Okay. What's clear here is that when the maximum speed is at 50 to 65 bits, the link capacity is 4,500 to 6,000. Then for the calibration of the model, we loaded the known link flows as real flows into the network, as shown earlier by June. We know the link flows for AP Reyes, Hipodromo, JP Rizal, South Avenue, and Nicanor Garcia. And then the corresponding link IDs and their adjacency as to node IDs are shown also on screen. Now for the back and forth real flows on that links, we divide it by 2, assuming a directional distribution of equal. So 0.5, 0.5 on going to and going from. Okay, next slide. And then since the given data on real flow are in vehicle trips, so we need to convert it to equivalent passenger car. So we use a data from JICA MUECP as published by the National Transport NCTS, National Center for Transport Studies in UP Diliman. So here you have tricycle and motorcycle at equivalent passenger car 0.3, cars and taxi at 1, including the AUVs, multicabs at 1.3, as well as the Jeep, buses 2.5, trucks at 2. So in converting the total vehicle trips into its equivalent PCU, it is just 0.996 PCU per the total vehicle count. So based on the model share. So we assume the model share as constant. Okay, next. And then for the link performance, that result would be as follows. The average flow is at 330 PCU per hour. And then at a total average congestion level at 14.48%. And a network delay of 0.773. So this would be the base scenario. So not yet at 2030. This is at 2023, year 2023.
Minimum is 34%.
Sir?
Congestion level, maximum congestion level, 34%.
34, yes.
Okay.
It occurred at can you go back to the slide at the net showing the network? Here. It occurred at between nodes 1 and 2 here.
Oh, okay.
The one closest at the no, it's at 1 and 8, between nodes 1 and 8. The links 13 to 14. So it is fairly close to the circuit development. And then it's 34, but the links between nodes 1, 2, 3, 4, and 6, those are at 24% to 30%. So the greatest or the higher congestion levels occurred at this at that section near the circuit development.
So at this point it's low.
Yes, sir. Yes, sir. So we'll see if if we progress based on the future growth rates, would the same phenomena be observed? Okay, for the future scenario, I will turn the floor to Joe Ben.
Thank you, sir. So for the future scenario, sir, can we proceed with the next slide? So based from the base scenario presented by Sir Vin, we predicted the flow and PCU conversion for 2030 So using the base scenario, we use the growth rate method. The factor that we use came from the population a while ago that was presented by Sir Jun. So here is the future flow and PCU from each of the nodes and links. I mean the links
Yeah.
for the future scenario. So, sir, so here is the data.
Okay.
So can we proceed with the next slide? So these are the 35 links as presented by Sir Vin a while ago in the future scenario. So next slide, please. So using the data from the future scenario, okay, we also run a model through IFN and it gave the same result as the base, which is the maximum congestion occurred at links link that connects 1 and 8 and 8 and 13 as same as Servin. So from here we thought of three alternatives which will be presented. So can we proceed with the next slide? So here is the summary or the parameters that can be seen from the future scenario. It's almost the same as Servin with the base scenario. It's around 30% the maximum congestion, which also occurred at links that connects links 1 and 8, and then it will be seen here. Can I annotate? Here, sir, is the maximum. 36. So it increased because we increased the what we can say as the demand since it's a future prediction. So from here we proceed with the alternatives, sir. Can we move to the next slide? Okay. So our proposed traffic management intervention, we considered the first alternative, additional lanes to Pascua, Ipodrimo, and Isobel. We chose this streets, sir, because these are the streets with the congestion level of 30% or more. As estimates, sir, since they are the highest, we will move with these streets to be added a link. So what will be the result? Then the second alternative that we did is the suggestion you did, sir. You said to us, sir, that what if we try to reduce one lane to certain links? So what we did, sir, for alternative 2, since all the links that was presented in alternative 1 are already one link only, so we search for links that has greater than 1 you call this link road, and we reduce one lane. Okay. But considering that those roads should have less congestion level. For these two roads, Kalayaan Avenue and JP Rizal, these roads have 4 lanes. And their congestion levels around only 5 or 6 or 7, just like that. It's ranging from that percentage, sir. So we tried to reduce one lane to this road, sir. That's alternative 2, sir. And the third alternative, can we proceed? What if we try to use a combo? We implement alternative 1 and alternative 2 at the same time. So that's our third alternative, sir. So can we proceed? The simulation, sir, for alternative 1. So that's what I said a while ago. We added for this simulation, we just added 1,500 to the link capacities of the roads that we considered to be added, to have additional lanes. And from here, as we can see from a while ago, this link was part of the maximum congestion, these 2 links. But after running this alternative 1, it was transferred to this link or this, sir. But the value, sir, is lesser compared to the maximum a while ago, sir. So that's the first alternative, sir. We will give the summary later, sir, so we can check. So that's what we did in alternative 1. Next is alternative 2. So alternative 2, we reduce lanes. Actually, sir, the lanes that was reduced is here and here, sir. This part. Okay. So that was the 2 links that was reduced. So those lanes was reduced by 1,500. Their link capacities was reduced by 1.5. And retaining the data from the future, retain the flow from the future scenario, input it in the model. See, and it remains that this link and this link is still congested, sir. But relatively, somewhat better, somewhat lang, little bit only. Okay, sir. Then the last alternative, the combination, so we will we shown the 3 simulations, and this time the maximum congestion is same as the alternative 1. It was transferred to another road. Okay, sir. So can we proceed with the summary, sir?
Yes.
That's just the table of this alternative 3 from the summary table of the future and the alternatives.
So
Next slide.
interesting, you can see that once you apply certain combination of the alternative, the congestion is moved to somewhere else.
Yes, sir. So can we move, sir, to the summary? Next slide.
So is there any question to this group from other
There.
groups? Yeah.
So here's the summary of our simulation, sir. So the flow, the network travel distance, and the network SIP are relatively the same from the scenarios, the future and our alternative, sir. So relatively the same. And can we move to the next comparisons? There. We focus on the congestion level, sir, and the delay. From the future scenario, sir, the maximum is 36%. So that's where we started. When we add lanes, it was the new maximum is 23.35, which is lesser than the future. And alternative 2 also lesser maximum value, and alternative 3 gave the least value for the maximum. But what we considered, sir, is the average, and so we can consider the whole road link network. So from the future scenario, we should be getting the alternative with a lesser value compared to the future.
Wait, before that, can I ask a question? Why your future scenario is still 36?
Sir?
Why your future scenario percentage? No?
Sir, the future scenario is
36.
the simulation, sir, from the for the 2030, sir. So here is, if this is the what we did, sir, in the future scenario, it is the scenario if we will not do anything to the road networks currently.
I mean, the base scenario is 36, but the future scenario is also 36.
36. I'll check, sir.
I mean, the current situation is 36, right? And then you project it to 2030, and you increase the trip generation.
Sir, it's 34, sir, the base scenario.
34. Oh, increase only little?
Based on our run through, sir.
Oh, even though the population increased like from 3,000 to become 100,000? Right, your population increased from 3,000 a while ago to 100,000+. But the congestion is also increased only like 2%. Yeah, and please check, no problem. Yeah, so
Okay, sir.
your method is okay. Yeah, I just wonder about the numbers.
Okay, sir.
I mean, the population increased so much, but why the congestion increased very little? That's something is missing in that area, isn't it?
We'll double check, sir.
Yeah, so please double check on that. Yeah. So
Okay, sir.
I mean, the whole method is fine. So only the numbers is probably need to check more detail.
Okay, sir.
So any other question or comments to these groups? Yeah. So once you double check on that numbers, so please publish your work. Okay?
Copy, sir.
I mean, in terms of the whole method and the work itself is very interesting. Yeah? So I just concerned with the numbers. It's a bit strange.
Maybe, sir, we'll gonna run the projection part of the future scenario.
Yeah.
We'll review that one.
Yeah.
Okay. Thank you for your
Yeah,
comments.
thank you. Thank you. So, okay, thank you. So, other groups, please. Who will present next? Joyce? Mark? Who will present next? Go ahead, Mark. Okay.
Sorry, I was with Juben's. I am with Juben's. I was about to present the conclusion recommendation
Okay.
for studies.
This one. So you are in the same group.
Yes, sir.
Yeah, that's fine.
Okay.
Other group. So who is the other group? Len. And Joyce. Yeah. So what happened? Leslie?
Sorry, Glycerin and I will present our topic.
Okay.
Hi, sorry. Can you see my screen?
Yeah, yeah.
Uh, our topic is about the case study on the Route 2 and the Libreng Sakay program of the Quezon City Bus program.
Mm.
So we discussed already the data up to this one. So we'll proceed with the analysis approach that we did, which unfortunately when we were discussing earlier, we found out that um we had the computation wrong. So
Um,
for this one, for a while. For this one, we have the annual average daily traffic of uh 407,000
oh,
for Commonwealth
okay.
in 2023. And then what we did based on our related literature is multiply it to 10% just to have a conservative estimate for peak hour traffic. Oh. And then we also assigned 60%, 40% split on the busy direction volume.
This is not enough. 8 lanes times.
Sorry, and
Yeah.
yes, sir. And then after which um we estimated the number of lanes that are operational along Commonwealth. So that gave us 8 and road capacity of 1,900 based on what's one of the RLs that we did. So based on the computation that we had, which we realized was wrong when you were discussing earlier, we had the volume capacity ratio of 1.61, which is greater than 1. And then based on this, we assumed that the capacity for Commonwealth is
Hmm.
falls under overcapacity.
Okay.
So um these are the uh analysis that we did based on the result that we had.
Yeah.
Um since there is a dominance of private cars based on the AADT that we got from MMDA, it highlighted the challenges of the non-public transport vehicles taking up much of the road capacity and limits the buses that move freely along the stretch. Then after which we assess the bus operations based on the fleet size, the daily trips, and the passenger capacity per bus. So we got a total of 737 capacity for all trips, and we compared it with the number of the average ridership that we had, and we based on the comparison that we did, we found out that there was only reduction in in that number of trips on Saturdays, but the computed congestion along Commonwealth did not seem to affect the service of the number of trips that's existing. And then we also did a short route observation. And oh, sorry, this is just a photo that we got over the internet, but this is Route 2, and we noticed this for um infrastructure observations that we did that we noticed along the route. Glycerin will explain the approach for sensitivity analysis.
So for this section, we conducted the sensitivity analysis for Route 2. So the analysis quantifies the impact of various scenarios on congestion levels by evaluating changes in the base scenarios or the key variables such as the traffic volume, road capacity, and the public transport share. So we conducted 3 scenario analysis, which is the reduced peak hour percentage to 8% of the AADT, the increased peak hour to 15%, and we assume one lane closure along the route, which reducing the capacity to 15,200 vehicles per hour. And scenario 4 is this increase of public transport along the route. Next slide, please. And then we'll after conducting the scenarios, we'll evaluate the VCR for each one. So for under baseline conditions, as mentioned earlier, it's calculated at 1.61, exceeding the threshold of for severe congestion that will be tackled later. We set baseline for severe free flow threshold, severe congestion threshold, and critical threshold. So for peak hour traffic volume, for baseline, the peak hour traffic volume is at 40,799 vehicles per hour, or the 10% annual AADT of the vehicles. So at scenario 1, the reduced peak hour traffic, the first scenario reduces peak hour traffic to 8% of AADT, lowering peak traffic volume to 22,521 vehicles per hour. So this resulted to a VCR drop of 1.48, which under the severe congestion threshold. While this reduction is congestion is slightly along the route, it does not achieve free flow conditions, which the one we set is at 1 VCR. And for scenario 2, the increased peak hour traffic at 15% of the AADT. So the VCR climbs at 1.85, indicating critical congestion. So the scenario reflects the increase of private vehicle dependency without effective with the increase of private vehicle. This resulted to the increase of the VCR under severe congestion. For scenario 3,
Can I ask, what is this is just changing your assumption, isn't it?
yes, sir.
So
So
from 10% to 8%, and then what is
yeah, we
percent?
just assume certain percentages
Right.
for the reduce and increase
There is
peak.
no real control here. This is just your
Yes, sir. It's just comparison of
this
based on our RRL.
okay. Sensitivity analysis is okay, but this is not really your policy, isn't it? This is no policy at all.
No, sir.
Yeah,
Just
so
comparative
just
analysis.
comparative analysis. Okay. So this should not be policy analysis. No? So these two are the policy analysis that you create.
Yes, sir. For scenario 4, scenario 3, we simulated the impact of the reducing the road capacity by reallocating one lane in each direction exclusively for the libreng sakay buses. So this we assume a decrease of the peak hour traffic. So we minus one minus one lane. So that's 38,899 peak hour traffic vehicle per hour. So with still high traffic volume, the VCR at 2.55, and for the last scenario, increase of public transport share. But at this one, we're not sure at our the peak hour traffic vehicle per hour. So what we did was just less 12% of the base scenario. Then
So based on your computation here, I'm not sure if your number here is correct.
yes, sir.
What
Yes.
your base is 10%, and then suddenly you
Yeah.
increase to 38% by
No. The one at the baseline, that's from the BC direction volume.
But
So
why improving the number of lanes and public transport actually increase the traffic? It's supposed to reduce, not increase, right?
yes, sir, but we're not sure actually if we're going to consider the peak hour traffic 10% that we got from the AADT or the BC direction volume with 60-40 split from the peak hour traffic.
The assumption must be the same. Don't change the assumption.
Okay. So from the baseline,
Right. So
uh,
say the baseline, it depends on your baseline. So you can assume 10, you can assume whatever, but then you don't change the assumption in the alternative. Okay. Once you change the assumption, you cannot compare, isn't it?
okay, so we'll just change the numbers to the baseline data.
Right. So in fact, this one, no need, this one. Huh?
Yes, sir.
So you can put these numbers in the baseline if you want.
Okay, sir.
Okay.
And next slide.
Yes.
Just a graph of the VCR scenarios.
Okay. So in this case, do you want to present it again? So you do the rework of your work. I think there are a lot of error in this.
Yes, sir.
Do you want to have some more time, and then you can present it
Yeah.
separate?
Yes, sir. We're gonna ask for an extension for the
No.
paper also, but we're willing to present it again.
Yes, please. Because there are a lot of error in this case, even the policy and the result of analysis. No?
Yes, sir.
So let's set up the time that you want.
Okay, sir. Thank you, sir.
So,
Yes, sir.
okay. And if you need some consultation, we can set up also appointment.
Yes, sir. Thank you.
Okay.
We'll email you for the time.
Okay. So next is Joyce and Gab.
Let me screen share, sir. Wait.
Yeah. Go.
Right.
Hi, sir. Hi, everyone. Can you hear me po?
Yes, please.
Yes. Sorry, I cannot turn on my video. I can turn on for a bit just to say hi, because maybe I will get disconnected if I continue showing the video. Um, this is our final project. This is traffic impact assessment for the MetLive 3. This is a project in Pasay City. So later we're gonna check again the location. This is for me, Gab, Nev, and Victor. Unfortunately, the other members have engagements tonight, so they cannot join. So some of the analysis are done by them. So we'll try to answer, but maybe we can also present together with the whole team after. I think we also have some more things to do after or comments. Gab, can you get to the next slide? Okay. So just like any other projects or developments, MetLife 3 is supposed to contribute to the economy, but of course, it shall be influencing the traffic patterns, hence the warrant for the traffic impact assessment. So this is just a figure of the proposed mixed-use development in Pasay. So varying towers, and it's mostly residential. Next slide. So the total floor area is around 250,000 square meters, and 32,700 or 30,800 is the square meters is the total land area. So the total number estimate of dwelling units is actually 1,813. So shown there is also the target launch and completion. So the number of actually is around 200, almost the same, and the project pesos. Next. Sorry, next. Ayan. Again, the objective of the report is to forecast traffic impacts and changes in the traffic volumes, and to recommend a certain mitigation measure. Scope and limitations were only limited to 1 kilometer radius, so that will also be shown later what intersections those are. And it is less limited to just the development of the MetLife 3. Next. These are just some literature review, of course, the TIA, the traffic conditions, levels of congestions. Next slide. This is the conceptual framework, of course, data collection, which will lead to the existing condition, and forecasting and computation, the impacts, and recommendations. Next. We conducted traffic count survey on November 3 morning on the peak hour. We considered peak hour 8 to 9 p.m. So it is for 2 intersections that will be shown as we discuss the result later. And secondary data on various economical and project data from the agencies or the project itself are collected for the analysis. Next, I think this is my last slide. So this is just to show the 1 kilometer radius. So that is the MetLive 3. And of course, we have various intersections there. I think you're familiar with the EDSA as well as the Rojas Boulevard.
Right.
So next, Gab, I think it's your part. Thank you.
Yep. So as mentioned, the 1 kilometer radius from MetLive includes the Macapagal Avenue station and the EDSA station of the LRT and MRT. So as you can see in the picture in the left side. And then the breakdown of vehicles per direction from the data we collected. So westbound, that's 27%, northbound 25%, eastbound 23%, and southbound is 24%. So almost the same. However, the only difference is mostly the vehicles that pass by these roads were mostly private cars. So next are the PUVs, motorcycles, and lastly are the trucks. So predominantly, mostly private cars are dominant in the area. So which is also why we included that in our recommendation. We took that into account for our recommendation. Yeah. So as I mentioned earlier, these are the data points. Actually, these are just the numbers now. So a while ago, I just showed the percentages. So northbound and southbound, heavier traffic due to EDSA being a major arterial road connecting north and southern Metro Manila. Not to mention that it also leads to numerous roads, including going to Manila and Valenzuela, and from south, from Makati and Parañaque. And the eastbound and westbound, significant but lower volumes, providing access to commercial areas like the Mall of Asia complex. And during peak traffic volume, this occurs during the rush hours of 7 to 9 a.m. and 5 to 7 p.m. with high vehicle counts in both northbound and southbound directions due to the activities being done in the MOA area. Right. So in its final development, so MetLife 3 may be expected to produce almost 4,388 daily person trips. So that's the trips that we're projected to produce, and then we're projecting that it will attract more than 2,756 daily person trips, being primarily a residential development, seen to generate more trips from within, from its residents, compared to the trips likely to be made by visitors and staff coming from outside the area. And to add, so we also created the prescribed minimum parking slots in connection with the MetLife 3's generated trips. The 2005 implementing rules and regulations of the National Bidding Code provides for a minimum of 1 parking slot for every 6 dwelling units, considering a minimum size of at least 50 square meters per unit for high-rise residential buildings. So this has been factored into the analysis, being a proposed development of 1,800 units, which must provide at least 303 parking slots. But our recommended number of parking slots is 1,830, since the total number of units are 1,830. So to conclude, actually the parking slots equivalent to the number of dwelling units for both residents and visitors and general cars users in the area. And introducing alternative modes of transportation such as cycling and also improving the pedestrian in the area can also improve transportation and movement of people. Increase public transport capacity through more vehicle units or through more frequent trips. And since predominantly jeepneys and buses are the main modes of transportation in the area, since it's a bit far from the train station. So I think it's better we interconnect cycling and walking with the buses and jeepneys to provide more options for residents in the area. Yep. That's our presentation.
That's all. So you did not make any control. You did not make any impact assessment. I thought.
Actually, sir, we're still finalizing that final output.
Okay. So this is science. This is not religion. Okay. So you cannot recommend something without analysis. The one that you conclude a while ago, all those recommendations are blah 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 without any analysis, without proof. this become religion already. This is not the way to do. Okay. So if you want to propose something, you need to analyze, and then based on your analysis, then you propose, isn't it? So you cannot just propose anything based on opinion, right? You need to do analysis, and then based on that analysis, you conclude. Okay. Otherwise, everyone can say anything. So in that case, we don't need the engineer, we don't need urban planners. Correct? So
Yes, sir. I think mostly we focused on for the study more. We focus more on the vehicle movements of the private vehicles, but I think we're also going to add the public transport system for
that's fine. So
for the
your
final.
numbers is correct. So it's more or less now. So 1,800. So it's about 275 and 300 parking. So I guess it's just adding small numbers to the traffic. Okay. Then the question is, you need to mitigate this. Okay. What is your proposed scenario based on this adding traffic? So what is your mitigation so that the congestion level may reduce, right? So then you need to analyze that. So I hope this is what you can do.
Okay, sir. We're still adding to the final
Okay,
final project for the final paper. Sorry.
right. So probably you want to present it again in that case. Complete group four person. Is that okay? So you can set an appointment. No problem.
Okay, sir.
Okay. So thank you very much. You have your final exam on the 13th in Moodle. So I open it from morning until evening. Okay. And please do all your final presentation before end of the year, so you can make an appointment so that we can give you the grading before end of the year. Is that okay? So thank you very much for the semester. Okay. I enjoy this class. Okay then. See you.
Thank you, Prof.
Thank you.
Sorry, excuse. Can I have a moment?
Please.
Yeah. So apologies in advance for this question because my specialization is not really transport planning, but I observed the way traffic analysis or modeling is done is very location specific. However, a traffic system of one location or area may be connected to a traffic system of another. So any intervention introduced in one area may affect the other. Also,
Right.
having these integrated traffic policies like in mega cities like Metro Manila, it seems to be counterproductive. So in a real road traffic planning or modeling, how is this being considered? And how are the differences in policies being considered? So personally, would you recommend having a harmonized traffic system and policies like in Metro Manila, which is composed of many different cities?
So very big question, Mark.
Sorry.
I agree with you. So we need to create an integrated system rather than just spot by spot. Okay. So as an urban planner, so you need to create the entire city plan. So one way to show you a while ago is if you can create closer to the pre-matching capacity in terms of network structure, that is one idea. Okay, and of course it must be integrated with other systems, including the land use planning, including the public transport system, okay, including the budgeting of the economic system. Okay. And most crucially is actually regarding the management, management
Yeah.
system, meaning that the trust issue between the employer and employees is the actual problem. So that's why a lot of work, which is actually just exchange of information. Okay, the employer require the employees to come to work.
Mm.
It is not necessary in the mega city. Okay, like Metro Manila. So the work that actually exchange information, you don't need to come to the office. That will greatly significantly reduce the traffic congestion and also the flexible work hour, for example. So working through, so as a government, okay, you need to combine the Ministry of Information with Ministry of Transportation. Okay, so it's not just separate issues. This is actually integrated issues. You see, because the way we think is separate. That's why become sectoral.
Right.
Right. So I hope you can start to make the noise in this area. Then we start to see. Maybe you can help on that part. No?
Yeah, I think there are already some people who are calling for, harmonizing traffic rules in Metro Manila, but I don't know if they're being heard.
Mm.
I don't know, maybe some of my classmates have something to say about it because they are more transport. Anyway, thank you for that answer,
Yeah,
sir.
thank you. Thank you. So, okay, so thank you very much for the semester. I hope you can give feedback also about this class. So
Yeah.
anything that we need to improve for next time, so you can just tell.
Yeah, thank you also, sir. I actually enjoyed, even though this is not really my thing, because my specialization is
Yeah.
environmental planning.
Okay.
So, but I really enjoyed. I have a lot of learnings.
Yeah.
Thank you, sir.
Thank you very much. Glenn, you want to consult today or next time?
Sir, if you allow us to extend
That's
a
okay.
little bit,
Yeah, sure.
Catherine and I will be staying.
Okay, sure.
We'll
So
ask.
the rest can dismiss. Go ahead.
Hi, sorry. Because during our formulation of the sorry, what's happening? The formulation of our methodology, we're Glazer and I are a bit confused because we know that we need to work on the network utilization of the road. But then again, our study is about optimization of the bus alone.
No, you
So
can
we
focus
can,
on bus, no problem.
sorry, sir.
You can
What was
focus
that?
on bus, yeah, no problem with that. You,
So during first consultation, I know that you have already instructed us what to do, but um we still don't know we still don't know how to proceed with the first analysis that we showed you earlier.
can you show it again? I don't know. Sure.
Sorry, sir.
Your slide.
Okay.
So your scenario is the problem. So you see here. No, this is fine.
With this one, sir, right?
Yes. No, before this. The four scenario that you propose.
No, I think this
That
is
one, that four scenario. So correct me if I'm wrong. So your proposed scenario is you have the baseline, which is 10% of AADT, right?
yes, sir.
Okay,
That's correct.
so I can accept that, no problem. It's here. And
No,
then
sir, the one that's no, the 24,480. I just forgot to remove the baseline because we first put there the baseline of the AADT, the 10%, but I changed it to the BC direction volume, which the one we
can you
did.
show slide number 12 in that case?
Yes, that one.
This one.
What?
Your ADT is 400,000, right?
Yes.
About 10% is about 40,000. And then
Yes, sir.
you split 60-40. So become per direction become 24,000 maximum, right?
Sorry,
Yes,
sir,
sir.
the 24,000 is the 60%.
Yeah, okay,
Able
that's
to show
fine.
the project.
So that one is now that's 60% of 24,000 you divide by 8 lanes. Is that correct?
Yes, sir.
Per direction is 8 lane or total is 8 lane?
The total number is, we assume operational is 8 lanes, sir. Per
Redirection.
direction.
Per direction, 8 lane.
Yes, sir. Yes.
So 8 times 2,000 is 16,000. So this is 24,000. This is larger than 1. Yeah, about correct. So this is the base analysis. That's okay. This is I can accept. And then
Okay, sir.
the next one.
And then
No, the scenario is
this is
what is this?
this is just for bus operations, but we will proceed with the sensitivity analysis, sir,
Oh,
because
wait.
that's where
The
you.
bus operation I can accept also that you need about 700 bus.
Yes, sir. Yes,
Okay.
sir.
Next one.
This is the sensitivity analysis,
Before
sir,
that,
where we
before this.
this one.
Yeah, okay. This is the one that strange. Your scenario 1 is reduce peak hour percentage to 8%. What is this?
That's just same from the next slide, sir.
No, what is the meaning of this 8% of IADT? You already said 10% and then you change it to 8%? And what is scenario 2? Increase peak hour percentage to 15% IADT. What's that?
We assume a percentage for the reduce and increase, sir.
Oh. Yeah, for sensitivity analysis, I understand. Between 8 to 15, that's what you want to say, right?
Yes, sir.
Yes, sir. From the base.
But this is not really something that you control. This is just sensitivity analysis for the sake of computation. So that you will see the bandwidth, right? From 8% to 15%, on average 10%. So this is the one that you need to consider. That's okay. So this is not scenario 1 and 2. Okay. So this is actually within sensitivity analysis, you have 3 scenarios. 8%, 10%, 15%. That's okay.
Okay, sir.
Right?
Comparison of the 3.
Yes. So comparison of the 3, that's fine. Okay. Next, the actual scenario that you have is actually scenario 3 and 4, which is actually scenario 1 and 2, isn't it?
Yes, sir.
Okay. So you have 6 box in this case, no? 8%, 10%, 15%, and then scenario 1 is assume 1 lane, and then scenario 2 is actually increase public transportation. So in that scenario, you assume suddenly 12%. No, you need to increase little by little so that you will know the optimum value.
So we
So-
should show the increment
Yeah.
going to 12%.
Actually, we already practiced that last week, remember?
Yes, sir.
In your one of your assignment. So that part, something that you control, that is become the scenario alternative, no? So you have a base scenario, which is current, and then you have alternative one, assume one lane, and as an alternative two is increasing of the public transport user. Oh, that one is okay, but your computation is strange. Can you show now the 16? See, your base is 24,000.
Sir, we weren't sure if we're going to use the BC direction volume or the 10% AADT.
No,
That's why.
you cannot change the assumption. If you want to compare
Sir,
10 with 10, 15 with 15, 8 with 8,
okay,
isn't
sir.
it?
Yes, sir.
If you change the assumption, then become confusing. You cannot compare,
Okay, sir.
right? So say I assume 24, okay? So let's say you are using this part, you will compute later, right? So let's assume this one first, okay, 24. So in this case, when you create one more lane, this is supposed to reduce than 24. The same thing with increase of public transport. This is supposed to reduce than this one. But even in you are using this number, why this is actually higher? This is strange. Okay, let's
used kinds of baseline, sir. That's why we were not able to actually get the same value for peak
okay.
hour.
So what baseline do you use in this one and this one? 15%?
No, sir, that's from the 10%.
Right. Oh, okay, say from the 10%, 24, and then you dedicate one lane, right, for the bus lane.
Yes.
And then how many people actually you have? See, this is 24,000 480. That is in vehicle per hour. Correct, yeah? So in that case, you
Yes.
need to compute the person trips. How many people actually use this? So you have the PCU values a while ago, and then the percentage, right? So you can convert back to person trips, isn't it? Not in vehicle per hour, isn't it? So you can return
sir.
back to person trips, and then now you change based on the percentage, the same number of person that you want to travel. Now you put it into bus. So one bus is like 30% instead of one car is 1.5 or 1.7 person per car. Okay, but the PCU value per bus is like 3. So one bus is like three times of car. So in that case, should reduce, not increase. Right?
Yes, sir. Yes, sir. Because we were not able to actually see the conversion part from vehicle hour to PCU, and also the assumptions that we used for the policies 1 and 2 were not the same as the baseline. So
Yes.
I think that's where we messed up.
Right. So the same thing, yeah, when you increase the public transport, because the same number of person trips, right? Okay. You need to convert back from vehicles to person trip first, because what you transport is the person, not the vehicles.
Yeah.
Correct, right? So the one that you make it fixed is the number of person, the demand, no? The person trips per hour must be the same. Then you distribute into the bus. This must be reduced, cannot be like this.
So it should be lower than that.
Yeah, should be lower than 24.
Because we weren't really sure if on our
The unit
so
should be in PCU per hour, not vehicle per hour.
yes, sir. We weren't able to convert it to PCU.
Yes. So that part is the I just number alone, yeah, we can start to see that this is known. I don't know the detail, but surely not possible to increase you.
I agree. We were also skeptical about this computation.
Okay. Please check again our assignment in PCU in mode choice. I hope you remember.
Yes, sir.
Yes,
I think you simulated from 0% to 100%. Okay. You did the assignment, right?
yes, sir. So, we can actually now realize that we can actually copy the um
Lecture from
process
a
that
while ago.
So
we can assume 10% to 100% transfer of passengers to buses. Is that what you're trying to say?
yes.
Yes, sir.
So
Yes.
and this one at what point it will be helpful, and then now you have the number of bus at that point. What is the VCR?
Yes, sir.
Right. So
Really.
but
Now we know where we got it from.
okay. You can focus on that.
And then
Yes.
yes, sir.
And then
Sorry, sir. And then after that, sir, that's since we're using those this two scenarios already, would that be enough for us to have policy recommendations already?
yes. So now you want to know what is the actual increase of public transport that you need. Not 12%, but what percentage that you need, right? And then for whether this one is better than this one, or actually combination of the two is better,
Okay, sir.
right?
Copy, sir.
Then you can
Yes,
propose.
sir. Now we know.
And then you can talk about sensitivity analysis. Now I have a 10%, 8%, 15%. At what point is actually so we don't know, right? Between 8 to 15%, we don't know which one. So that's okay. But at the most severe part, this is the case. The most improved part, this is the case. So then you can say your analysis is robust. So this
Copy,
is
sir.
just to tell that your analysis is considering a wide range of values. But the most important is actually the control part, the one that you can plan, not the assumption.
Yes, sir. Yes, sir. So is it okay, sir, if we don't proceed with this two,
Oh, that's okay also.
so that yes, sir, so that we can focus with the different percentages that we will allocate for the mode choice, sir.
Right. And then you can also proceed with this and then combine which scenario is actually the best one.
Yes, sir. Copy, sir.
Good.
Thank you, sir.
Thank you.
And then, sir, we'll just email you for the final presentation. We know we're late, but it's better that we submit a correct presentation.
Yeah, you can submit today, no problem, but you can resubmit later. There is no deadline.
Okay, sir.
Yeah,
Thank you, sir.
same
Thank you
order.
so much
But
for
you
your
just
call.
inform me, okay, so that I will know that you submitted again.
Okay.
Yes, sir. We will
We'd like to ask for another consultation before the final presentation.
Yes, when you finish this, so you tell me before the
Yes,
end
sir.
of the year. Is that okay?
Okay, sir.
before the end of the year. Copy, sir.
Yes, sir.
Thank you, sir.
I hope before Christmas.
Yes, sir.
Yes, sir. Thank you
Absolutely.
po.
Okay.
Thank you po.
Yeah. Yeah.
Learned so much from you.
Yeah, thank you. Okay, good.
Sir, so will today be the last day that the class will convene? So we're not meet on the 13th?
13 is no meeting, only exam.
Sir. Okay po.
So today is our last day.
Okay, sir. Thank you, sir.
Thank you.
Yes, sir. Bye.
Bye-bye. Yes.
Lecture in the lecture earlier, when generating the random numbers or for the capacity matrix, I don't think I'm getting the right
Sure,
uh
I can help you.
let me in the
N underscore.
and you right
Okay,
capacity.
there, random capacity. Just stop, stop.
Okay,
You just stop. Okay, there. Just close it.
close.
Okay, enter. And then
And then
that one you don't copy. You hold your shift key. Okay, and then just arrow to the right and to the bottom. Okay. Right.
Okay.
And then go here and in this to edit, click your mouse there. Okay, and then hold the shift and key, shift and control. Okay, hold, press that, and then enter.
Okay.
Oh, there.
Thank you, sir. That's my only problem a while ago.
Yeah.
Anyway, thank you, sir.
Okay. So once you have this, so remember whenever array operation in Excel, always the same thing. Okay, so you will see this is an array operation. There is a curvy bracket there. That one cannot be edited. If you want to edit, you need to delete everything.
Okay, sir. Thank you, sir.
After that, you continue, yeah, with the flow, with the congestion, speed, travel time, and so on.
Yes, sir.
Okay.
You're going to upload the recording, right, sir?
Sure, of course.
Yeah, thank you.
Yes. Thank you. Yes. Thank you very much. Vin, are you okay? Yeah. I will just close it. Okay.
Yes, sir. I just forgot to log out.
Okay.
Thank you, sir.
See you next time.